It is a quiet and constant feature of our reality. A cup of coffee, left on its own, will always grow cold. An egg, once scrambled, will never reassemble itself. A shattered glass will not leap from the floor, suddenly whole. Welcome to the science for deep sleep. If this kind of calm exploration into the universe helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. These processes seem trivial, the background rules of the world. But within them lies a connection to one of the most profound questions in physics: why time appears to flow in only one direction. Is this one-way passage a fundamental law of the cosmos, or is it an emergent property of the universe, and perhaps, of our own consciousness? This undeniable sense of forward movement is what physicists refer to as the arrow of time. It represents a deep asymmetry between what has been and what will be. The past is fixed, recorded in memory and in the fossil record, leaving only traces in stone. The future remains open, a realm of possibilities yet to unfold. We are carried along this current, from birth towards death, with no capacity to halt our progress or reverse its course. The source of this arrow, however, is a mystery. When we examine the fundamental laws of physics governing the smallest particles, we find something remarkable. They have no preference for the direction of time. The equations describing an electron's motion or a planet's orbit function equally well forwards as they do backwards. This raises a critical question. Why is our macroscopic world, the world of coffee and eggs and people, so irreversibly one-directional? This is the mystery we will now explore. It is a journey that begins with the familiar warmth of a coffee cup and leads to the most fundamental laws of thermodynamics. We will examine a cosmic contradiction, where the reversible rules of the small clash with the irreversible reality of the large. We will travel to the origin of the universe itself to find the source of this arrow, and even look within our own minds to understand how our consciousness is woven into this cosmic fabric. By the end, the simple act of a cooling cup of coffee will appear as a window into the deepest workings of reality. The thermodynamic arrow: why coffee gets cold. We can begin with the cooling cup of coffee. When hot, its molecules possess a high degree of kinetic energy, vibrating rapidly. The molecules in the surrounding air move, on average, more slowly. Through countless collisions, the faster coffee molecules transfer their energy to the slower air molecules. The coffee cools, and the room warms by an imperceptible amount. Eventually, they arrive at a shared temperature, a state of thermal equilibrium. We have never observed the reverse: a lukewarm cup of coffee spontaneously drawing heat from the air to become hot once more. The same principle explains the impossibility of unscrambling an egg. A whole egg is a system of significant order. The yolk is distinct from the white, its complex proteins folded into precise configurations. The act of whisking breaks down this structure, mixing the components into a uniform, disordered state. One cannot unwhisk the egg or spontaneously reform the yolk. A state of order has been transformed into a state of disorder. This one-way journey, from order to disorder, is the foundation of the arrow of time. It is known as the thermodynamic arrow of time *, and it is governed by one of the most powerful laws in physics: the Second Law of Thermodynamics. The second law states that within any isolated system, a quantity known as entropy will always increase, or at best, remain constant. It is never observed to decrease. Entropy can be understood as a measure of disorder or randomness. A tidy room is a low entropy state. A messy room is a high entropy state. It is easy to transition from tidy to messy as objects are moved and scattered. Reversing this process requires an input of energy to refold clothes and restack books, decreasing the room's entropy. However, in doing so, your body metabolizes energy, radiates heat, and increases the total entropy of the universe. The astrophysicist Arthur Eddington, who coined the term arrow of time in 1927, stated it with clarity. To find the direction of time, one need only look for the direction of increasing randomness. If a system is becoming more disordered, one is looking toward the future. The relentless increase of entropy is the physical process that paints a direction onto time. Consider a new deck of cards, arranged in perfect order by suit and number. This is a low entropy state. After shuffling the deck repeatedly, the cards become mixed and chaotic, a high entropy state. The probability of returning to the original, perfect order through shuffling is not zero, but it is so astronomically small that one could shuffle for the entire age of the universe and never expect it to occur. This is the key. A decrease in entropy is not forbidden by the laws of physics, but it is fantastically improbable. The movement from order to disorder is not a command, it is a statistical inevitability. There are simply vastly more configurations that correspond to a state of disorder than to a state of order. The universe, left to its own devices, will always drift towards the most probable state, which is the state of highest disorder. When cream mixes with coffee, the molecules intermingle. There are countless arrangements that we would recognize as mixed coffee. There is only one arrangement corresponding to a distinct blob of cream on top of black coffee. The system naturally evolves towards the state with the greatest number of possible arrangements, the high entropy state. The shattering of a glass functions on the same principle. There is one state we call a whole glass. There are trillions of states we call a pile of broken shards. The system falls from a state of low probability to one of high probability. This is the thermodynamic arrow of time. It is why ice melts in a warm drink and does not spontaneously reform. It is why smoke dissipates and does not gather itself back into a chimney. It is why our bodies age, their complex structures breaking down over time. These are all processes of increasing entropy, a march from a more ordered past to a more disordered future. This seems fundamental, yet when we look at the universe at its most basic level, the arrow appears to vanish. The microscopic reversibility, a cosmic contradiction? Imagine viewing a recording of a pendulum swinging in a perfect vacuum with no friction. It moves from left to right, then right to left, in a repeating arc. If this recording were played in reverse, it would be impossible to tell the difference. The reversed motion is just as physically plausible as the forward motion. The same holds for a recording of two billiard balls colliding. One ball strikes the other, and they scatter. Played in reverse, the scattered balls move toward each other, collide, and send the first ball back to its starting point. This, too, appears perfectly normal, obeying all the laws of motion. This is a deeply puzzling fact about our universe. The fundamental laws of physics, from Newton's laws of motion to the rules of quantum mechanics, are time-symmetric. The equations describing these interactions do not have a built-in preference for the past or the future. For these laws, time is a two-way street. The reverse of any physical process is, in principle, just as possible as the forward process. This is often called the reversibility paradox. Physicists in the 19th century, like Joseph Loschmidt, argued that if the velocity of every particle in a system could be reversed, the system should retrace its path, and entropy should decrease. We are thus faced with a massive contradiction. At the microscopic level, events are reversible. At the macroscopic level of our experience, they are not. How can a universe built from reversible components produce such an irreversible reality? The answer is found in the work of the physicist Ludwig Boltzmann, who showed that the second law of thermodynamics is a statistical law. It is not an absolute rule in the way gravity is. Returning to the cream and coffee, we have trillions of molecules. While it is physically possible for random molecular motion to separate the cream back into a single blob, the odds are so infinitesimally small as to be practically zero. It is comparable to flipping a coin a trillion times and having it land on heads every single time. It is possible, but it will never happen. Consider the air in the room you occupy. Is it possible for all the randomly moving molecules to suddenly move to one half of the room, leaving you in a vacuum? According to the laws of motion, yes. It would violate no fundamental law. But the number of ways the molecules can be spread evenly is unimaginably larger than the number of ways they can be compressed into one corner. The system will always evolve toward the state with the highest number of possible arrangements, the state of maximum entropy. Boltzmann's entropy formula, S equals K log W, connects entropy, S, to the number of microscopic arrangements, W, that correspond to a single macroscopic state. The value of W resolves the paradox. For a disordered, high-entropy state, W is a staggeringly large number. For an ordered, low-entropy state, W is a relatively tiny number. While any individual microscopic path is reversible, the overwhelming statistical tide flows in one direction, from the less probable to the more probable. From low entropy to high entropy. The arrow of time, therefore, is not a property of individual particles. It is an emergent property of a system with many particles, born from the statistics of large numbers. The one-way nature of time we experience is a consequence of our universe having begun in a state that was, against all odds, breathtakingly ordered. The entire history of the universe has been the slow, irreversible movement away from that initial state. To truly understand the arrow, we must go back to the beginning. The cosmological arrow of time, from Big Bang to heat death. The thermodynamic arrow of time points from the past to the future. This implies that the past must have been more ordered than the present. The further we go back, the more ordered things must have been. If we trace time back to the very beginning of the universe, we must arrive at a state of astonishingly low entropy. This is precisely what cosmological models suggest. The universe began about 13.8 billion years ago in an event known as the Big Bang. At that moment, all the matter and energy in the observable universe was compressed into an incredibly hot, dense, and uniform state. One might think a uniform soup of particles sounds disordered. In most contexts, uniformity is a sign of high entropy. However, gravity changes the calculation. In a system where gravity is dominant, like the universe, uniformity is a state of incredibly low entropy. Gravity is a force that pulls matter together. Over time, a smooth distribution of matter will be drawn into dense clumps, stars, galaxies, and galaxy clusters. A universe where all matter has collapsed into black holes would be a high-entropy state for gravity. Therefore, the initial, smooth, hot, dense state of the early universe was a state of phenomenally low gravitational entropy. It was like a perfectly formed, unbroken egg. This initial condition is what physicists call the *past hypothesis. It is the postulate that the universe began in this special, low-entropy state, and it is the ultimate source of the arrow of time. The Big Bang wound up the cosmic clock. The history of the universe since has been the process of that clock unwinding, of entropy increasing as the universe expands and evolves. This direction of time, linked to cosmic expansion, is the cosmological arrow of time. As the universe expands, structures form. Stars ignite, radiating heat and light, and massively increasing the entropy of the cosmos. Everything participates in this grand, one-way journey from an ordered beginning to a more disordered future. The thermodynamic arrow governing cooling coffee is aligned with, and ultimately caused by, this cosmological arrow. The ultimate future this arrow points toward is known as the heat death of the universe. As entropy continues its inexorable increase, stars will exhaust their fuel. Black holes will slowly evaporate over trillions of years via Hawking radiation. Eventually, all matter will decay into a thin, uniform soup of particles and radiation, all at the same near absolute zero temperature. In this final state of maximum entropy, no structure or energy gradients would remain. No complex processes could occur. Life as we know it would be impossible. In a universe at heat death, there would be no more arrow of time. With entropy at its maximum, the distinction between past, present, and future would dissolve. This leaves us with the deepest mystery. Why did the universe begin in this special, low entropy state? The laws of physics do not seem to require it. Statistically, a messy, high-entropy beginning is far more likely. The origin of our universe is, from a statistical standpoint, a profound anomaly. Some physicists believe this is the most significant unanswered question in cosmology. Theories like cosmic inflation attempt to explain how such a state could arise, but they too rely on certain initial assumptions. For now, we are left to know that we exist in the aftermath of a highly improbable, ordered beginning, and this fact is what gives time its direction. The psychological arrow of time. Why we remember the past. We have discussed the arrow of time in thermodynamics and cosmology, but there is another arrow, one that is far more intimate. The psychological arrow of time. This is our subjective experience of time's unidirectional flow. We possess memories of the past, but not of the future. We feel that we move through a succession of moments, from a fixed past toward an open future. Physicists such as Stephen Hawking have come to believe that the psychological arrow is not separate from the thermodynamic arrow, but is a direct consequence of it. A memory, in physical terms, is an ordered pattern of information in the brain, a specific network of neurons. To form a memory, the brain organizes a chaotic stream of sensory input into a coherent, ordered trace. This process requires energy. The brain is a chemical machine that consumes ordered energy, food, and, in the process of thinking and forming memories, releases disordered energy, heat, into its environment. The very act of forming a memory is an entropy-increasing process. A small pocket of order is created in the brain, but at the cost of a greater increase in the total disorder of the universe. We remember the past because it is the direction in which entropy was lower. We create records of a more ordered state. We cannot have memories of the future, because the future is, by definition, a state of higher entropy and greater disorder. It has not yet been recorded, it exists as a sea of probabilities. This leads to a profound conclusion. Intelligent life can only exist where there is a strong thermodynamic arrow of time. To live, process information, and think, an organism must metabolize, it must consume ordered energy and dissipate it as disordered heat. A being in a universe at thermal equilibrium could not exist. Therefore, our psychological arrow of time must point in the same direction as the thermodynamic arrow. You remember the past and not the future because you are a physical process coupled to the universe's overall increase in entropy. Our consciousness does not observe the flow of time from the outside, it is an expression of it. We are eddies in the current of increasing entropy. This also explains our perception of cause and effect. The cause precedes the effect, a process that creates correlations and increases entropy. We can influence the future by creating new correlations, but we cannot influence the past, where those correlations are already fixed. The one-way nature of causality is another manifestation of the second law. Your personal timeline is a small reflection of the grand cosmological timeline, launched from the Big Bang and pointing toward the eventual heat death of everything. Modern twists and unanswered questions. The model of entropy increasing from a low-entropy Big Bang is the standard framework for understanding time's arrow. But science continues to probe this mystery, proposing new and sometimes radical ideas. One of the largest remaining questions is the past hypothesis itself. Why did the universe begin in such a special state? Some physicists find the answer, that is simply how it was, to be unsatisfying. One fascinating, though speculative, idea is the Janus point model, proposed by the physicist Julian Barbour. He suggests the universe may have a central point of maximum order, from which time flows in two opposite directions. In each branch, the universe expands and entropy increases. For inhabitants of one branch, time moves forwards, while the other branch would appear to be in their distant past, running backwards. In this view, the arrow of time is not a property of the entire universe, but a feature of the half we happen to inhabit. Another frontier is the quantum world. Some physicists believe the arrow's deepest roots may lie in quantum mechanics. A process called quantum decoherence, where an ordered quantum system irreversibly loses its properties upon interacting with a disordered environment, could be a fundamental source of time's direction. Recent theoretical research even suggests that at the most fundamental level, opposing arrows of time might emerge. While this does not imply time travel, it hints that the forward flow we experience may not be the only possibility. Experiments have even managed to locally and temporarily reverse the thermodynamic arrow for a small number of quantum particles, causing heat to flow from a cold object to a hot one by exploiting quantum correlations. This shows that the arrow of time is a statistical law, not an absolute one. These ideas are on the cutting edge of theoretical physics. They all attempt to explain the arrow of time not as a given, but as an emergent feature of a deeper reality. As the physicist Sean Carroll has noted, the arrow of time might be analogous to the concepts of up and down. In deep space, these directions are meaningless. But here on Earth, our proximity to a massive object creates a powerful local asymmetry. Similarly, our place in the universe, in the aftermath of a low-entropy Big Bang, creates the powerful temporal asymmetry we experience as the arrow of time. We return to where we began, with a simple cup of coffee, now lukewarm. This mundane observation is a quiet, constant reminder of a profound cosmic story. We have seen that this is the thermodynamic arrow of time, the march of entropy from order to disorder. We have examined the paradox that the fundamental laws of physics are reversible, and found the resolution in the power of statistics. That a decrease in entropy is so improbable we will never witness it. We traveled back to the origin, to the cosmological arrow, launched from a state of impossibly low entropy at the Big Bang. The entire history of our universe is the story of this initial order slowly unraveling. And finally, we saw how we are part of this process. Our psychological arrow, our ability to remember the past but not the future, is a direct consequence of the physics of entropy, a necessary condition for the existence of conscious life. The arrow of time is a collection of arrows, thermodynamic, cosmological, and psychological, all flying in formation, all launched from the same cosmic event. It is not a fundamental law, but an emergent property, a consequence of our universe having a very special past and the statistical tendency of all things to drift towards the vast landscape of probable futures. The shattered glass remains broken. The coffee remains stirred. Our memories are of what has been. But now, when we see these things, perhaps we will see them for what they are. Quiet reminders of our place in a grand cosmic unfolding, a story of order, chaos, and the relentless, one-way flow of time. Physics explains why you can't remember the future. Think about your brain for a second. It's this intricate, living archive, able to store decades of your past. Every joy, every sorrow, every boring Tuesday morning is catalogued in staggering detail inside you. You can recall the taste of a meal from years ago, the smell of your childhood home, the exact words of a conversation that's long gone. This library in your head holds an incredible amount of data about what has been. But have you ever wondered why, with all that storage space, you can't access a single second of your future? Why can't you remember what you're going to have for breakfast tomorrow with the same clarity that you remember this morning's coffee? It feels like a glitch in our biology, right? A weird quirk of how we evolved. But what if I told you this isn't a limitation of your mind, but a fundamental, non-negotiable law of the entire universe? What if the reason you can't remember the future is the exact same reason a shattered glass will never leap off the floor and reassemble itself in your hand? The same reason a drop of ink in a glass of water will never unmix itself? The same reason an egg can't unscramble itself back into a perfect, pristine shell? This isn't a mental block, it's physics. The future is locked away from you by a cosmic principle that governs everything from the tiniest particles to the biggest galaxies. It's a law that dictates the relentless, one-way flow of events we call time. And that law has a name: entropy. Today, we're going on a journey to the very edge of time to understand this profound idea. We're going to unravel why your past is a fixed, accessible record, while your future is an ever-branching storm of beautiful, chaotic mystery. This isn't just a physics lesson. It's the story of why your life only moves in one direction. The mystery of the one-way street. Our entire experience of reality is built on a rule so simple we never question it. Time moves forward. We are born, we live, we get older. Coffee gets cold, buildings fall apart, stars burn out. Effects always follow their causes. We call this forward march the arrow of time. But here's where things get weird. If you zoom all the way down to the microscopic world, to the fundamental laws of physics that run the universe, that arrow just vanishes. The most basic rules of nature, from Newton's laws to the bizarre equations of quantum mechanics, are almost perfectly time-symmetric. What does that even mean? Well, imagine watching a video of two billiard balls colliding. Looks normal. Now, play that video in reverse. The collision itself, the impact and the rebound, still looks completely plausible. It perfectly obeys the laws of physics. If I only showed you the reversed clip, you'd have no idea it was being played backward. The fundamental laws just don't care which way time is flowing. Take it even further. A planet orbiting a star looks just as valid in reverse. An electron zipping around a nucleus follows rules that work equally well forward or backward. The microworld, the very foundation of our reality, is a two-way street. So, why isn't our world a two-way street? Why does our everyday experience so violently contradict the fundamental nature of things? Why does a video of a shattered glass reforming look so obviously wrong, like a cheap magic trick, while the shattering itself is completely normal? Something is creating that direction. Something is taking the reversible laws of the micro-world and forcing them into an irreversible, one-way story on our scale. That something isn't a force like gravity. It's a principle of probability. A law of statistics so powerful it dictates the fate of the entire universe. It is the second law of thermodynamics, and its main character is entropy. To understand why you can't remember tomorrow, we have to understand this universal tendency for things to fall apart. We have to understand why order always, inevitably, gives way to disorder. The universal law of mess. Let's forget physics for a second and talk about your bedroom. Imagine you spend an hour making it perfectly tidy. Everything is folded, stacked, and arranged. This is a state of low entropy. You can think of entropy as just a measure of disorder or randomness. When your room is tidy, it's highly ordered, so it has low entropy. There are only a few ways for your room to be perfectly clean. Now, just live in that room for a week. You toss a shirt on a chair, leave a book on the floor, kick your shoes into a corner. The room gets messy. Its entropy increases. And here's the key. There are vastly more ways for your room to be messy than there are for it to be clean. Clean is one specific arrangement. Messy is, well, it could be billions of possible arrangements. The shirt could be on the bed, or the floor, or the desk. The shoes could be anywhere. The universe doesn't have a preference for clean or messy. But because there are overwhelmingly more ways for things to be messy, it's statistically almost guaranteed that your room will slide from that one, rare, orderly state into one of the countless, common, disorderly states. A messy room isn't caused by a messiness force. It's just probability. This is the core idea that the brilliant and tragic physicist Ludwig Boltzmann figured out in the late 19th century. He realized that entropy is basically a count of the number of ways you can rearrange the atoms of a system, the microstates, and still have it look the same on the outside, the macrostate. Let's use a deck of cards. The macrostate could be a new, ordered deck. There is only one microstate for this: ace of spades, king of spades, and so on, in perfect sequence. Just one way. Now, consider the macrostate, a shuffled deck. How many ways can you arrange the cards to get that? The number is astronomical. It's 52 factorial. That's an 8 followed by 67 zeros. It's a number so huge it makes the number of atoms in our galaxy look tiny. So when you shuffle a deck, you're just letting it fall into one of the trillions upon trillions of more probable, messy arrangements. Is it possible to shuffle a new deck and have it land back in perfect order? Yes. Is it likely? No. It is so mind-bogglingly improbable that if you shuffled a deck every second since the beginning of the universe, you wouldn't even scratch the surface of all the possible combinations. This is the second law of thermodynamics. In a closed system, entropy, disorder, tends to increase over time, simply because there are vastly more ways to be disordered than to be ordered. An egg shatters into a mess because there are countless ways for its molecules to be arranged as goo on the floor, but only one specific way for them to be a whole egg. A hot cup of coffee cools down because its concentrated heat energy, an ordered state, spreads out into the trillions of air molecules in the room, a more disordered, higher entropy state. The energy doesn't vanish, it just scatters into a more probable arrangement. This isn't a strict rule, it's a statistical one. It just says that the overwhelming probability is that things will get messier. An egg could unscramble itself. The right vibrations and heat could conspire to push all the molecules back into the shell. But the odds of this happening are so low you'd have to wait for trillions of times the age of the universe to see it. The arrow of time, that one-way street, is just the universe moving from less probable states to more probable states. It's the relentless march towards higher entropy. And the reason time has this direction is that it started in a very, very special way. To understand that, we have to go back to the beginning. The cosmic blueprint. The second law explains why time flows from order to disorder. But this brings up an even deeper question. If the universe is always getting messier, why wasn't it just born a mess? If maximum entropy is the most likely state, why didn't the universe just start there and stay there? This is one of the biggest mysteries in physics. The fact that we exist, that stars form, that life can evolve, it all depends on one unbelievable fact. The universe began in a state of extraordinarily low entropy. At the Big Bang, 13.8 billion years ago, the universe was incredibly hot and dense. You'd think a hot, dense soup of particles would be a total chaotic mess, a state of high entropy. But when you factor in gravity, the most powerful force in the cosmos, the picture flips. In a system ruled by gravity, a smooth, uniform spread of stuff is actually a very low entropy, highly ordered state. Why? Because gravity likes to pull things together. Over time, a smooth gas will naturally start to clump up. Tiny differences in density will grow, pulling in more and more matter, until you have huge areas of empty space punctuated by dense, hot clumps. We call those clumps stars and galaxies. So, a clumpy universe like ours today is actually a higher entropy state than the smooth soup of the early universe. The messiest, highest entropy state for our universe would be for all its matter to have collapsed into black holes. Compared to that possibility, the hot, uniform plasma of the Big Bang was almost perfectly ordered. The universe was basically born, with its room perfectly tidy. It was handed a deck of cards in pristine, new deck order. This initial, highly improbable, low entropy state is what physicists call the past hypothesis. It's the anchor for the arrow of time. We don't have a full explanation for why the universe started this way, but we know that it did. This is the crucial step. The second law says entropy increases. But that only means something if you have a low entropy starting point. The Big Bang was that starting point. It set the universe on a one-way trip, a cosmic journey from the super-ordered past, through the clumpy present, toward a future of maximum disorder. This cosmic increase in entropy is the asterisk thermodynamic arrow of time. It is the master clock for the whole universe. And as we're about to see, our own psychological experience of time, our ability to remember the past and not the future, is completely tied to it. The story of the universe is also the story of your mind. The brain is a time detective. So, we have a universal arrow of time, driven by entropy's relentless increase since the Big Bang. Now we get to the heart of the question. How does this stop you from remembering the future? The answer is in figuring out what a memory physically is. A memory, whether it's a footprint in the sand, a fossil, a photograph, or a pattern of neurons in your brain, is a physical record. It's a structure that exists now that is correlated with something that happened in the asterisk past. And the key feature of any record is that it's a pocket of relative order, a low entropy structure that holds information. Think of a crater on the moon. It's a record of an asteroid impact. The crater today lets us infer a past state, a smooth surface and an incoming rock. This works because we instinctively use the past hypothesis. We know the moon started off in a smoother, lower entropy state. The impact increased the total entropy by throwing off heat and debris, but it left behind an ordered trace. The crater, that tells a story. Your brain does the exact same thing, just with chemistry. When you form a memory, your brain makes a physical trace. It strengthens certain connections, builds new proteins, and creates a neural pathway that represents the experience. This pattern is a highly ordered, low-entropy state. And creating this order doesn't violate the second law. In fact, it's a perfect example of it. To create that tiny pocket of order in your brain, your body has to burn energy. It's metabolically expensive. It takes the ordered energy from your food and pumps out a much larger amount of disordered heat into the world. So, the total entropy of the universe, you plus your surroundings, still goes up, keeping the second law happy. But in the process, a stable, low-entropy record is left behind in your head. Memory is a process that works with entropy. We can make records of the past because the past was in a simpler, lower-entropy state. In a way, the past is easy. It happened. Out of all the chaotic possibilities, one path was taken. One set of events occurred, leaving a trail of evidence. The past is a single, determined story. Now, compare that to the future. Why can't you have a record of the future? Because the future hasn't happened yet. It doesn't exist as a single, simple state. The future is a vast, branching fog of high-entropy possibilities. While the past is a single point, the future is an expanding storm of maybes. Think about trying to remember tomorrow's lottery numbers. For you to have a memory of them, a specific, ordered pattern of neurons would have to form in your brain today. But which numbers? There's no single, determined future event to make a record of. The future is a chaotic mix of all possible outcomes. There's no cause from the future that can reach back in time and create an effect, a memory, in the present. That would require the universe's total entropy to spontaneously go down, like a shattered glass reassembling itself. It would be a statistical miracle. We can predict the future, but that's totally different from remembering. Prediction is just using what we know now to make a statistical guess about the most likely high-entropy outcome. We predict a storm because we see the low-pressure system. We predict where a ball will land because we know its speed and the force of gravity. But these are just calculations about a chaotic future. They don't have the solid certainty of a memory, which is a record of a determined, low-entropy past. Our brains even seem to be built to process this arrow of time. A fascinating 2022 study on salamander retinas showed that the way their neurons fired in response to moving images was irreversible. The cells' interactions created their own tiny arrow of time, a signature of entropy being produced right there at the cellular level. This suggests our very perception of time's flow might be built into the way our neurons work, a direct result of the same thermodynamic arrow that governs everything else. So, the psychological arrow of time, our feeling of moving from a known past to an unknown future, isn't an illusion. It's a direct consequence of the thermodynamic arrow. Your brain is a physical system. It follows the same laws as a star. It can create records of a low-entropy past by increasing the messiness of its surroundings. It cannot create records of a high-entropy, probabilistic future, because there's nothing definite there to record. You can't remember the future because the universe hasn't decided what it is yet. The future is a blank page, not because you're out of ink, but because the paper itself is still a chaotic storm of disconnected fibers. The edge of time. This link between memory, entropy, and the Big Bang is an incredibly powerful explanation. But like all great ideas in physics, it comes with its own mind-bending paradoxes and wild frontiers that scientists are still exploring today. One of the first challenges came from Boltzmann's own colleague, Joseph Loschmidt. He came up with the asterisk reversibility paradox. He argued that since the basic laws of physics are time-reversible, you could, in theory, just reverse the velocity of every single particle in a system, and it should perfectly retrace its steps, causing entropy to asterisk decrease. So why do we only ever see it increase? The modern answer comes back to that past hypothesis. While a state that leads to decreasing entropy is physically possible, it would require an unbelievably fine-tuned and correlated arrangement of particles. Think of a breaking glass. To reverse it, every single shard, every vibrating air molecule, and every bit of heat would need its velocity perfectly reversed to push the glass back together. It's not impossible, just so colossally improbable that it's never going to happen in a universe that started off in a simple, orderly state like ours did. The arrow points forward because the starting line was special, not because the laws of physics are a one-way street. Then you have the quantum world. The main equation of quantum mechanics, the Schrödinger equation, is also time-symmetric. And yet, the act of measuring something seems to be irreversible, collapsing a cloud of possibilities into one definite outcome. This measurement problem, and its link to the arrow of time, is one of the deepest puzzles in modern physics. Some theories even suggest that every quantum measurement is a tiny, entropy-increasing event that helps lock in the arrow of time at the most fundamental level. And finally, out on the truly speculative edge, you have physicists like Julian Barbour. His Janus point theory proposes something wild: that the Big Bang wasn't the asterisk beginning of time, but a central point of minimum messiness, like the narrowest part of an hourglass. From this Janus point, time could actually flow in two opposite directions. In this scenario, there could be a twin universe on the other side of our Big Bang, experiencing time flowing in the opposite direction from us, where their entropy is also increasing relative to their start. The arrow of time we feel would just be a matter of which side of that central point we happen to live on. It's a mind-bending idea that challenges everything we think we know about time. These frontiers show that while entropy gives us a powerful reason for our experience of time, the story isn't over. The questions get deeper, but they all point to the same incredible conclusion. Our most intimate, personal experience, the feeling of moving through time and making memories, is written into the cosmic DNA of the universe itself. We started with a simple question: why can't you remember the future? And the answer took us from a cooling cup of coffee to the time-symmetric laws of the quantum world. We saw how the sheer force of probability turns that microscopic two-way street into a macroscopic one-way arrow, a law we call the Second Law of Thermodynamics. We traveled back 13.8 billion years to discover the ultimate source of that arrow, the Big Bang. An inexplicably ordered, low-entropy state that set our entire universe on an unstoppable journey from order to disorder. And we saw that our own minds aren't separate from this cosmic story. Memory isn't magic, it's physics. Our brains create tiny, ordered records of a determined past, and pay for it by increasing the total disorder of the universe. We remember the past because it was simple. We can't remember the future because it's a chaotic, high-entropy storm of what might be. Your inability to remember even 1 second into the future isn't a flaw in your design. It's a direct, inescapable consequence of the same physical law that governs the death of stars and the fate of the cosmos. It's the signature of entropy, the echo of the Big Bang, ringing through every moment of your life. You are a creature of time, built to surf the relentless, ever-increasing wave of entropy, a detective, piecing together clues from a low-entropy past, while looking forward into the beautiful mystery of a high-entropy future. So, the laws of physics seem to create this one-way flow for time and memory. But let's speculate. If you could have a memory of a future event, what would that imply about the universe? Would it mean the future is already written? Or that you somehow exist outside of time's flow? Let me know your most creative, mind-bending thoughts in the comments below. Why time only flows forward? An ice cube on a warm day will melt. We watch it lose its form, its sharp edges softening into a clear puddle of water. It is one of the most common events in the world. But have you ever witnessed the reverse? A puddle of water, sitting in the sun, that suddenly gathers itself together, shivering and rising back into a perfect, crystalline cube. Of course not. It feels fundamentally wrong, like a film played in reverse. And yet, according to the most fundamental laws of our universe, the rules that govern every atom in that puddle, there is nothing that forbids it. At the smallest scale, the process is entirely reversible. So why does time seem to move in only one direction? Why do we see eggs scramble, but never unscramble? Why do we remember the past, but not the future? The answer to this question is not found in some exotic theory, but in a simple observation about the universe itself. It's what physicists call the arrow of time, the quiet, relentless, and universal sense that time only flows forward. The solution is hidden in the very nature of cosmic messiness. The reversible world. To understand the puzzle of time's arrow, we first have to look at the world of fundamental physics. It is a world that is, perhaps surprisingly, time-symmetric. At the most basic level, the laws of nature do not have a preference for the direction of time. Imagine a recording of 2 billiard balls colliding. One rolls across the table, strikes the other, and they move apart. Now, imagine watching that recording played in reverse. The 2 balls move toward each other, collide, and one continues on while the other comes to a stop. It would look slightly unusual, but physically plausible. If you did not know which was the original, you would have no way to tell. The laws of motion that govern them work just as well forwards as they do backwards. This is not a quirk of billiard balls. This is the reality for nearly all fundamental interactions. An electron repelling another electron. A photon of light being absorbed and then re-emitted by an atom. These tiny, elementary processes are all time reversible. The equations used to describe them remain valid if time were to run backward. This creates a paradox. The building blocks of our universe operate with a kind of temporal symmetry. Yet the world we build from them, the world of people, planets, and melting ice cubes, is governed by a strict, irreversible flow. Things break, but they do not unbreak. We age, but we do not unage. So where does this asymmetry come from? If the rules for individual particles are reversible, why is the larger game they play so fiercely directional? It is a discrepancy between the microscopic and the macroscopic world. To solve it, We must move beyond the behavior of individual particles and begin to think about the behavior of vast numbers of them. We need to introduce the concept that bridges this gap: entropy. The nature of entropy. The answer to the paradox is found in a single, powerful concept: entropy. It is often described as a measure of disorder or messiness. The astrophysicist Arthur Eddington, who famously described the arrow of time in 1927, was one of the first to connect the one-way direction of time to this idea of increasing randomness. The core idea is statistical. Things do not have an innate desire to become messy. It is simply that there are vastly more ways for things to be in a messy state than in a tidy one. Consider a bedroom. In a perfectly clean state, every object has one specific place. Books are on the shelf, clothes are in the dresser, shoes are in the closet. This is a highly ordered, low-entropy state. There is only one arrangement that we define as perfectly clean. Now, consider a messy room. The books could be on the floor, under the bed, or on a chair. Clothes could be in a pile or draped over a desk. There are not just a few ways for the room to be messy. There are millions, even billions of possible arrangements. This is the statistical heart of entropy. A system will tend to move toward a state of higher entropy because there are more of those states available to it. It is not a force, but a matter of probability. We can apply this to a physical example. When perfume is first sprayed, its molecules are clustered in one corner of a room. This is an ordered, low-entropy state. As the molecules move and collide randomly, it is statistically improbable that they will remain in that small corner. It is overwhelmingly probable that they will spread out, distributing themselves more or less evenly throughout the room. There are countless arrangements that we perceive as mixed, but only a very small number that we would perceive as unmixed. The system moves from order to disorder because it is settling into the most probable outcome. The same logic applies to a deck of cards. There is only one new deck order. But the number of possible shuffled arrangements is 52 factorial, a number with 68 digits. Every time you shuffle a deck, you are almost certainly creating an arrangement of cards that has never existed before. The ordered state is one in a sea of disordered states. This is the essence of entropy. It is statistics on a cosmic scale. Systems do not seek disorder. They simply stumble into it because the state of disorder occupies nearly all the possible configurations available. And this statistical certainty is what drives the arrow of time. Entropy in action. Now that we understand entropy as statistical messiness, we can look at the physical law that governs it, the second law of thermodynamics. It states that in any isolated system, the total entropy will never decrease over time. For any real-world process, it will almost always increase. An ice cube is a low-entropy state. Its water molecules are locked into a highly ordered, crystalline lattice. When this ice cube is placed in lukewarm water, a process begins as a direct consequence of the second law. Heat energy flows from the warmer water to the colder ice, not because of a desire, but because it is statistically more probable for the energy to be spread out. As energy flows into the ice, the water molecules in the crystal vibrate until they break free from their ordered positions. They begin to move around freely, mixing with the other liquid molecules. The highly structured system of the ice cube has become a disorderly liquid. The entropy of the system has increased. Could this happen in reverse? Could the water molecules spontaneously slow down, arrange themselves back into a perfect crystal, and push their excess heat into the surrounding water? Microscopically, any single collision is reversible. But for this to happen on a macro scale, it would require an unfathomable number of molecules to coordinate their random motions in a precise, anti-statistical way. It would be a spontaneous decrease in total entropy. The second law tells us this is, for all practical purposes, impossible. We see this principle everywhere. A hot cup of coffee cools as its heat spreads into the air, increasing the overall entropy of the room. An egg scrambles because its neatly folded protein molecules unfold and tangle into a chaotic mess. There are vastly more ways for the proteins to be tangled than for them to be perfectly folded. The system moves to a higher entropy state. The breaking of a glass, the rusting of iron, the erosion of a mountain. These are all irreversible processes. They are all journeys from a state of relative order to a state of greater disorder. They are all expressions of a single, directional process. The arrow of time, then, is simply the arrow of increasing entropy. This connection, from our kitchens to the cosmos, is what makes this exploration so compelling. The deepest truths about our universe are often found in quiet, everyday moments. If you find value in this journey of understanding, consider subscribing. We explore these large questions every week, and we would be glad to have you as part of our community. The cosmic story. We have established a connection. The flow of time is a consequence of the second law of thermodynamics. Time moves forward because entropy always increases. But this raises a deeper question. If the universe is on an inexorable slide towards maximum messiness, it must have begun in a state that was, against all odds, incredibly neat. For time to have a direction, the universe must have started in a state of remarkably low entropy. This is precisely what our best cosmological model tells us. Approximately 13.8 billion years ago, the entire observable universe was in a state of unimaginable density and heat, a scorching, uniform soup of particles and energy. One might think a hot, uniform soup sounds chaotic and messy, a state of high entropy. But here, we must account for gravity. In a system without gravity, like perfume in a box, a uniform distribution is indeed the messiest, highest entropy state. But in a universe governed by gravity, the opposite is true. Gravity pulls things together. Over cosmic time, the most probable, highest entropy state for a universe of matter is for that matter to be clumped together into massive, dense objects, black holes. A smooth, uniform distribution of matter in a self-gravitating universe is actually a highly ordered and very low entropy state. The early universe was just this, a perfectly balanced, exquisitely smooth, low entropy state. This is sometimes called the past hypothesis. The entropy of the universe at the Big Bang, compared to what it could have been, was infinitesimally small. Ever since that initial moment, the universe has been unwinding. It has been journeying from that initial order toward ever-increasing disorder. The arrow of time was fired at the moment of the Big Bang. The expansion of space created more room, more possible states for matter and energy to occupy, allowing the universe's messiness to grow. The smooth soup began to curdle under the pull of gravity. Tiny fluctuations in that initial smoothness grew over eons, forming the first stars and galaxies. Stars themselves are engines of entropy. They take ordered fuel like hydrogen and convert it into heavier elements, releasing enormous amounts of disordered heat and light into space. This massively increases the overall entropy of the universe. Everything that followed, the formation of planets, the emergence of life, is part of this cosmic unfolding. Life itself may appear to be a pocket of order in a universe tending towards chaos. But living organisms maintain their internal order by consuming low-entropy energy, like sunlight or food, and expelling high-entropy waste, like heat. We are like intricate whirlpools in a river flowing steadily downstream, temporary, beautiful patterns that exist only because the universe as a whole is flowing from low entropy to high entropy. The melting ice cube on a countertop is a local echo of this 13.8 billion-year-old process. The reason you experience time moving forward is because you are carried along in this cosmic current, a journey from a special beginning toward a future of ultimate, maximum messiness. We began with a simple puzzle. Why an ice cube melts but never unmelts? We found that while the laws governing individual atoms are time-symmetric, the statistical reality of large numbers is not. The second law of thermodynamics states that the total messiness or entropy of the universe only increases. An ice cube melts and an egg scrambles because these are journeys toward states of higher probability and greater disorder. This relentless increase in entropy is what gives time its forward momentum. The arrow of time is the arrow of increasing entropy. This led us to the origin of that arrow, the Big Bang. Our universe began its life in an exquisitely ordered, low-entropy state 13.8 billion years ago. Ever since, it has been expanding and unwinding, progressing toward a state of greater cosmic messiness. Your very perception of time is a consequence of your place within this grand journey from primordial order to ultimate chaos. But in answering one mystery, we uncover another. We have an explanation for why time has an arrow. But we have no explanation for why the arrow was fired in the first place. Why was the universe born in such a highly improbable, ordered state? Why this special beginning? This is, perhaps, one of the largest unanswered questions in cosmology. We have unraveled the secret of time's flow, only to find it points back to an even deeper enigma about the moment of creation. What are your thoughts on this journey? Let me know in the comments below. Why you can't unbreak an egg and what it reveals about time. On the smallest scales we can measure, the basic rules of physics don't seem to have a preference for the past or the future. Many of the most fundamental laws that govern reality work the same forwards as they do backwards. A planet moving through its orbit would look just as natural if we ran the film in reverse. Two billiard balls colliding and parting ways is a scene that makes perfect sense whether you play it forwards or backwards. So why can't you unbreak an egg? We've all seen it happen. The slip from the counter, the crack, and the splatter. It's an irreversible moment. You can't gather the yolk and the white and put them back inside the shell. This simple observation from our kitchens points to a quiet but profound question in science: the arrow of time. Why does time seem to move in only one direction? Why do we have memories of the past, but not the future? The answer, it turns out, leaves a trace in the messy, disordered state of that broken egg. It's a journey that will take us from the kitchen to the very beginning of the universe, and it stretches the idea of what time itself might be. The world according to physics, a two-way street. To understand this puzzle, we first need to see the world as the founders of modern physics did. For someone like Isaac Newton, the universe was a predictable, mechanical place. Planets moved in defined orbits and objects moved through the air, landing exactly where his equations predicted they would. The foundation of this mechanical universe is a set of laws, for motion, for gravity, that are largely time-symmetric. This means the laws themselves don't contain a forward direction. If you were to record a simple physical event, like a single ball bouncing off a wall, a physicist watching the recording would have no definitive way to know if you were playing it forward or in reverse. Both would look equally plausible, both would obey the laws of nature. Most of the fundamental laws of physics we've discovered, from Newton's mechanics to Einstein's relativity and even much of quantum mechanics, work the same forwards as they do backwards. There are some very subtle exceptions. A specific process involving the weak nuclear force was shown to have a one-way nature back in 2012. But for the world we see around us, for things like billiard balls colliding or planets orbiting a star, the rules seem to be time-symmetric. On the microscopic scale, the universe appears to have no set direction for time. And yet, our world is nothing like that. Our reality is a one-way experience. Buildings crumble over centuries. Dust doesn't spontaneously gather itself into a building. A log burns into ash. We never see a pile of ash draw in heat and light from the room to reform a log. And a whole egg, a complex and structured object, can shatter into a chaotic mess, but the reverse never happens. This is the paradox. On one side are the fundamental laws of physics, which are mostly reversible. On the other is the world we live in, where processes are relentlessly irreversible. It's as if the universe is built from parts that have no preference for time's direction, yet the world we experience moves only one way. The clue, it turns out, is not in the laws of motion. It's in the mess. The evidence, a broken egg. Let's return to our central piece of evidence, the broken egg. To a physicist, this isn't just a mess, it's a shift between two different states. To see why, we need to introduce two ideas: macrostates and microstates. A macrostate is the large-scale description of something, what we see. For the egg, we have two obvious macrostates: whole egg and broken egg. But a microstate is where the details matter. A microstate is the precise, specific arrangement of every particle in the system. It's the exact position and motion of every molecule in the shell, every protein in the yolk, and every water molecule in the white. It's a staggering amount of information, completely hidden from our view. Now, here is the key insight. Think about the macrostate, whole egg. How many possible microscopic arrangements of all those particles still count as a whole egg? The atoms can vibrate and shift slightly, but they are highly constrained into a specific, organized structure. The number of ways to arrange trillions of atoms and still have something you would call a whole egg is limited. Next, consider the macrostate, broken egg. The yolk is splattered, the white is spreading, the shell is in pieces. How many possible microscopic arrangements fit this description? The number is astronomically, almost incomprehensibly, larger. The molecules can be in a near infinite variety of positions, and we would still call it a broken egg. The transition from a whole egg to a broken egg is a journey from a state with a relatively small number of possible arrangements to a state with an enormous number of possible arrangements. The universe, it seems, has a powerful tendency to move toward states that have more arrangements available to them. And the name we give to this property, this number of possible arrangements, is entropy. The suspect, introducing entropy. The story of entropy begins not in a modern lab, but during the Industrial Revolution. In the 19th century, engineers building massive steam engines wanted to know how to get the most possible work out of their fuel. This practical question led scientists to a fundamental discovery about the universe. The German physicist Rudolf Clausius, studying the flow of heat, noticed that heat always flows from a hotter object to a colder one. It's why hot coffee cools down to room temperature. The energy spreads out, disperses, until it's evenly distributed. It never spontaneously gathers from the cool air to make a cup of coffee hotter. Clausius gave this process of dispersal a name: entropy. He then formulated what we now call the Second Law of Thermodynamics. Albert Einstein would later consider it the supreme law of all the sciences. In its simplest form, the second law states that in any isolated system, the total entropy, the total disorder, will either increase or stay the same. It never decreases. This is one of the most reliable observations we have ever made about the universe. Things wear out, they decay, they break, they move from a state of order to a state of disorder. So, let's define entropy again. More precisely, it is a measure of the number of ways a system can be arranged. High entropy means there are many possible arrangements, which we see as disorder. Low entropy means there are few possible arrangements, which we see as order. Now we can look at our egg again. The whole egg is a low entropy state. Its atoms are in a very specific, ordered arrangement. There are comparatively few ways for an egg to be whole. The broken egg is a high entropy state. Its atoms are in a disordered mess. There are vastly more microscopic ways for an egg to be broken. The breaking of the egg is a demonstration of the second law of thermodynamics. The system moves from a low entropy state to a high entropy state. But this still doesn't fully explain why. Why this constant movement towards disorder? For that, we need to meet Ludwig Boltzmann. A law of probability. Ludwig Boltzmann was an Austrian physicist who gave us a deeper understanding of what entropy really is. He looked at the second law and proposed something different. He suggested it isn't a rule of force, like gravity. It's not that some invisible barrier prevents the egg from reassembling. Instead, he argued, it's a law based entirely on statistics. On chance. The universe doesn't prefer to be messy. It's just that there are vastly more ways for it to be messy than there are for it to be tidy. A system isn't being pushed toward high entropy. It is simply moving through all of its possible configurations, and by sheer numbers, it is overwhelmingly more likely to end up in a state we would describe as high entropy. Think of a deck of cards, ordered perfectly by suit and number. This is a low entropy state. There's only one specific way for the cards to be in that order. Now, shuffle the deck. What is the probability that, just by shuffling, you will return the deck to its original, perfect order? It's not zero. It is possible. But the number of possible scrambled arrangements for 52 cards is enormous. An 8 followed by 67 zeros. It's a number so large that you would never expect to see it happen, even if you shuffled for the entire age of the universe. For all practical purposes, it's impossible. This is the secret of the second law. It's not that an egg can't unbreak. The laws of physics would allow for all the molecules of a shattered egg to happen to move in just the right way to reform the shell and leap back onto the counter. The problem is that the number of ways for an egg to be broken is so colossally larger than the number of ways for it to be whole that the odds of the reverse happening on its own are effectively zero. So, the second law isn't a command. It's a statistical certainty. The universe evolves toward higher entropy simply because high entropy states are vastly more numerous and probable. The arrow of time. This statistical movement toward disorder is the key to the arrow of time. The astrophysicist Arthur Eddington was the one who gave this one-way flow its name. He argued that the direction in which entropy increases is the direction we perceive as time moving forward. Think of any process that defines a direction in time. A cup of coffee cooling, a building eroding, a star burning its fuel. Every one of these is a process that increases the total entropy of the universe. The forward direction of time is, quite literally, the direction of increasing disorder. This even helps to explain the nature of memory. Why do we remember the past, but not the future? From the perspective of time-symmetric laws, this is a deep puzzle. The answer seems to be that the very act of forming a memory is an irreversible process. When your brain creates a memory, it organizes neurons into a specific, ordered pattern. But to do this, your body must burn energy. You consume ordered, low-entropy fuel, food, and release disordered, high-entropy waste, heat. That small island of order created in your brain comes at the cost of a much larger amount of disorder released into the universe. The total entropy goes up. A memory is a record of a past, lower entropy state. We can have records of the past because the past had lower entropy. We can't have records of the future because the future is the direction of even higher entropy. There's nothing to record yet. Our perception of time, our memories, and our sense of cause and effect are all consequences of the second law. But this raises an even deeper question. If the universe is always getting messier, that must mean that in the past, it was less messy. And if you go back far enough, it must have started in a state of incredible order. It begs the question, why was there an unbroken cosmic egg to begin with? The cosmic question, the unbroken egg of the universe. We've traced the arrow of time from a kitchen counter to the statistical nature of reality. But now we face the ultimate origin question. The fact that coffee cools and we age is all based on one huge assumption: that the universe began in a state of very low entropy. This is what physicists call the past hypothesis. It's the idea that the arrow of time exists only because the universe had a specific kind of beginning. And that beginning was the Big Bang. About 13.8 billion years ago, our entire observable universe was compressed into an incredibly dense and hot state. This early state was, perhaps counterintuitively, a state of incredibly low entropy. This can seem confusing. We think of a hot, dense state as chaotic. But in the context of the whole universe, the most powerful force for creating disorder is gravity. Gravity pulls things together into clumps, into stars, galaxies, and black holes. A smooth, uniform distribution of matter, like the early universe had, is actually a very special, gravitationally ordered state. It has immense potential to become clumpy and disordered later on. The Big Bang, therefore, was like the universe's perfectly whole, unbroken egg. It was a state of exquisite order and low entropy. And for the last 13.8 billion years, the story of the cosmos has been the story of that egg, breaking, in slow motion, as the universe unfolds into its more probable, higher entropy states. The arrow of time that we experience is a direct consequence of that beginning. The reason you can't unbreak an egg is, in a very real sense, because the universe started with the Big Bang. Life, complexity, and the price of order. A natural question arises from this. What about life? A human being is an incredibly ordered and complex system. A seed grows into a tree. Doesn't this process of creating order violate the second law? This is an important point, but it overlooks a crucial detail. The second law applies to isolated systems. Living things are not isolated. We are open systems, constantly exchanging energy and matter with our environment. To build and maintain the incredible order of your body, you consume ordered energy from your surroundings, the low-entropy chemical energy stored in food. In the process of living, you convert that energy into high-entropy waste, mostly heat, which you release. The decrease in entropy inside your body is paid for by a much larger increase in entropy outside your body. The total entropy of the universe goes up. So life doesn't defy the second law. It exists as a temporary and local feature because of it. You could see living things as intricate, swirling patterns in a great current of energy, one that flows from the ordered beginning of the universe toward its disordered future. It is a process that uses the flow of energy from order to disorder to power its own beautiful, temporary complexity. This journey, from a simple question about an egg to the grand story of the cosmos, shows how everyday observations can be connected to deep truths about reality. All of this stretches the idea of what time itself can be. And it makes you wonder what other deep truths are hiding in the quiet, everyday world around us. Let us know your thoughts in the comments. And if you enjoyed this exploration, make sure to subscribe so you don't miss our next journey into the questions of science. The end of time? The heat death. If the arrow of time is defined by the increase of entropy, where is it all going? This question points to a possible, though incredibly distant, future, the heat death of the universe. As entropy continues to increase, the universe will become more and more disordered. Stars will burn out. Galaxies will slowly dissipate. Even black holes are thought to eventually evaporate over unimaginable timescales. Eventually, the cosmos will approach a state of maximum entropy. This is a state of perfect equilibrium. Everything, everywhere, will be the same temperature, just above absolute zero. All usable energy will have been spent. All matter will have decayed into a thin soup of particles spread evenly across a cold, dark, and empty space. In this universe, nothing changes. And if nothing changes, time itself may lose its meaning. The arrow of time, driven by the flow from order to disorder, would cease to exist. There would only be a final, unchanging state. It is the ultimate broken egg. A state of permanent disorder. We started with a simple question. Why can't you unbreak an egg? We found the answer is connected to the largest story we know. It's because the universe had a beginning that was, for reasons we are still working to understand, in a state of extraordinary order. That initial low-entropy state is the ultimate source of the arrow of time. The one-way flow we experience is a law of probability, a statistical certainty born from those unique starting conditions. The shattering of an egg on a kitchen floor is a small echo of the universe's 14 billion-year journey from that initial, perfect state toward ultimate disorder. And here, the story takes a different shape. As the physicist Sean Carroll has pointed out, we shouldn't think of this process as just decay. A universe that had already reached its final, unchanging state of maximum entropy would be a universe where nothing could happen. It is the asterisk process of entropy increasing, the slow breaking of the cosmic egg, that allows for anything interesting to occur. It creates the flow of energy that powers stars, drives evolution, and allows for the intricate existence of life and consciousness. The arrow of time is the price of complexity. It's the cost of having a story. So the next time you see a broken egg, you're not just seeing a mess. You are seeing a trace of the beginning of the universe, the engine of all change, and the quiet, irreversible, and beautiful unfolding of time itself. The universe's greatest mistake created your future. Think about your life for a second. It moves in one direction, doesn't it? A relentless march from yesterday to tomorrow. You can't skip to the last page of your life, and you definitely can't go back and tweak the last chapter. Every single moment you've lived is now locked away in the past. You can remember it, sure, but you can't go back. This one-way street of time feels like the most basic rule of our existence. It's the beat of your heart, the tick of a clock. It feels absolute. But what if I told you that this entire experience is built on a cosmic technicality? That deep down, at the most fundamental level, the laws of physics don't actually care about past or future. To them, an egg reassembling itself is just as natural as it shattering. So, what's going on? Why are we stuck on this one-way trip? The answer is one of the biggest stories in all of science. It's a story about a single, massive, flaw, right at the beginning of time. A cosmic blunder so wildly improbable it just shouldn't have happened. This is the story of how the universe's greatest mistake created your future, and to understand why you can't remember what you're doing tomorrow, we need to rewind all the way to the beginning. The unbreakable law of yesterday. Just think about your morning. You woke up, maybe you made some coffee. You watched the grounds turn the water dark, and that's a one-way process. The steam rose from the cup and vanished into the air, never to return. You remember all of this in a straight line. Cause, then effect. The alarm went off before you opened your eyes. This is the unbreakable law of your reality. It's so obvious we barely think about it. The astrophysicist Arthur Eddington gave it a name back in 1927, the arrow of time. It dictates everything in our world. It's why buildings crumble but don't spontaneously rebuild. It's why embers cool down but never just glow hot again on their own. We are all prisoners of this forward momentum, swept along a river that only flows one way. And this isn't just a feeling, it's a fundamental law of science called the Second Law of Thermodynamics. It sounds complicated, but it's basically the universe's official rule for its one-way street. It says that systems tend to go from a state of order to disorder. Picture an egg falling. It shatters into a mess. That's an irreversible process. You will never see those pieces fly back together and the egg leap back into your hand. Why? Because there's basically one way for an egg to be whole, but there are trillions of ways for it to be a mess on the floor. The universe is a game of statistics, and it always bets on the outcome with the most possibilities. The messy, shattered state is just way more probable. This constant slide towards the messiest, most probable state is what we experience as time. The reason you can't unspill your coffee is that you're living in a universe that is relentlessly falling toward its most likely version. Every moment is just another step down that ladder of probability. This arrow of time seems like the ultimate rule. But it's not. When we look at the universe's rulebook, we find a shocking betrayal. The great cosmic contradiction. Here's the paradox that has kept physicists up at night for decades. On one hand, everything we see screams that time only moves forward. But on the other hand, the fundamental laws of physics, the very rules that run reality, say the complete opposite. At the tiniest, most fundamental level, almost every law of physics is time-symmetric. This means the equations don't have a preference for which way time is flowing. Running the clock forwards or backwards makes no difference to them. Imagine watching a video of two billiard balls colliding. One hits the other, and they fly apart. Now, watch it in reverse. They fly towards each other, collide, and one zips off. Both versions look totally plausible. That's because the laws of motion governing them work perfectly in either direction. This isn't just for billiard balls. It's true for Newton's laws of gravity, Maxwell's equations for light and electricity, and even the heavy hitters of modern physics. Einstein's theory of general relativity is time-symmetric. And Schrödinger's equation, the heart of quantum mechanics, is also time-symmetric. This is the great cosmic contradiction. The basic building blocks of our universe play by rules that are totally indifferent to past and future. Yet, when you put them together to make bigger things, like this, a powerful arrow of time just emerges out of nowhere. How is that possible? How can a universe built from time-reversible parts only go one way? It's like building a car where every single component works equally well in forward or reverse, but the finished car can only drive forward. It makes no sense. So if the laws of physics aren't creating this arrow of time, what is? The answer lies not in the rules, but in the starting conditions of the game. The universal law of messiness. To get our heads around this, we need to talk about a concept called entropy. It's often just called disorder, and that's a decent start, but it's more accurate to think of it as a measure of probability. It's the number of ways you can arrange something without changing its overall look. Let's use an analogy. Imagine a brand new deck of cards, perfectly ordered from ace to king, sorted by suit. There is only one way for it to be in that perfect order. This is a very low entropy state, specific and improbable. Now, give it a good shuffle. How many ways can the cards be shuffled? The number is insane. It's 52 factorial, and 8 followed by 67 zeros. Each one of those shuffled messes is a high entropy state. There are just vastly more ways for something to be disordered than ordered. The second law of thermodynamics is really just a reflection of these overwhelming odds. Things naturally drift towards the states that are most probable. They move toward higher entropy. This is why a sandcastle gets washed away into a mound of sand. There's one state we call sandcastle, but countless states we call mound of sand. It's why a drop of ink spreads out in water. The state where all the ink molecules are clumped together is just one arrangement, but the state where they're spread out is one of a massive number of possible arrangements. This, right here, is the engine driving the arrow of time. An egg shatters and doesn't reassemble because the shattered state has vastly higher entropy. The universe is unstoppably moving from less probable arrangements to more probable ones. From order to disorder. From low entropy to high entropy. This idea is kind of terrifying. It means every ordered thing, from a star to you, is a temporary, low-entropy arrangement fighting a losing battle against a statistical tide of messiness. The arrow of time is the story of the universe's slow decay into a state of maximum probability. But hang on. If the universe is always running downhill, from order to disorder, what does that mean about its starting point? It means if you go all the way back to the beginning, the universe must have started in a state of the most perfect, unbelievable order. And that is the great cosmic mistake. The improbable beginning. Following this logic of entropy is like following breadcrumbs back in time. If entropy always increases, the universe today is messier than it was a billion years ago, which was messier than it was 13.8 billion years ago. This leads to a wild conclusion. At the moment of the Big Bang, the universe must have been in a state of absurdly low entropy. This is the so-called blunder. The mistake your existence is built on. We tend to think of the Big Bang as a chaotic explosion. But in terms of entropy, it was the opposite. It was a state of almost supernatural perfection, an incredibly smooth, uniform soup of energy, with density variations of less than 1 part in 100,000. It was a state of supreme, mind-boggling order. To get how weird this is, think of our card deck. If a shuffling machine spat out a perfectly ordered deck, you'd assume it was broken. Now imagine finding that perfectly ordered deck on a barren alien planet right after an explosion. The odds are so astronomical you wouldn't know where to start. That's our universe. It was born in the most special, most ordered, most improbable state imaginable. The vast majority of possible starting points would have been a high-entropy wasteland, a universe born old and dead, full of black holes. But ours began in a pristine state, full of potential. This is the mistake, because it feels like a cheat. The universe shouldn't have started in such a special state. It should have been generic and messy. And yet, we are a direct consequence of this perfect start. This initial low-entropy state is the ultimate source of the arrow of time. Because the universe started so ordered, it had a downhill direction to roll, which allowed structure and complexity to form. Without this mistake, nothing would ever happen. No galaxies, no stars, no planets, and no us. Our future exists only because the universe had an impossibly ordered past. For years, this was the big mystery. Why? Was it just a freak accident? Or was something else going on? The answer, it turns out, is a beautiful plot twist that reframes the whole story. The gravity plot twist. For a long time, the low-entropy Big Bang was just accepted as a weird starting condition we needed to explain everything else. But what if the mistake wasn't a mistake at all? The key to solving this lies in a force we've ignored so far: gravity. Our intuition about entropy comes from things like gas in a box, where a smooth, uniform state is high entropy, it's messy. But for a system ruled by gravity, like a cloud of gas in space, the rules flip. For a self-gravitating system, a smooth, uniform distribution is actually a state of incredibly low entropy. Gravity loves to pull things together. Over time, a smooth gas cloud will clump up, forming stars and galaxies. This clumpy state, full of structure and empty space, is the high-entropy state for a gravitational system. The state of maximum possible entropy is a black hole. So, that perfectly smooth, uniform soup of the early universe? That wasn't a disordered state. From gravity's perspective, it was the most highly ordered, lowest entropy state possible. This is the big plot twist. The Big Bang's perfection wasn't a fluke. The universe had to start out smooth because you can't start with clumps. You have to start with the stuff that makes clumps. The ultra-smooth state was the ultimate blank slate, the point of lowest gravitational entropy from which the universe could begin its long journey of building structure and increasing its entropy by clumping things together. This insight helps us understand why there is an arrow of time. The initial, impossibly ordered state provided the potential for everything that followed. It's the downhill slope that the universe has been rolling along ever since, creating galaxies, stars, and us in the process. The universe with two futures. Now, this is where things get really wild. If the universe started at a point of minimum complexity, what does that imply about the direction of time? One speculative but fascinating idea, proposed by physicist Julian Barbour, is the Janus point theory. Barbour suggests that this point of minimal entropy wasn't the beginning of time in a traditional sense. Instead, he proposes it as a central point from which time flows in two opposite directions. Imagine it like the trunk of a tree. From the base, branches grow upwards into complexity. But from that same base, roots grow downwards, also branching out. The Janus point model suggests the universe could work like this. From this central moment of maximum uniformity, two arrows of time emerge. Two universes, each expanding away from a common point, each with its own, forward, flow of time, and each becoming more complex. In this picture, there could be a mirror image universe where time, relative to us, flows backwards. The inhabitants of that universe would experience their own Big Bang and their own arrow of time, just like we do. We just happen to be in one of the two rivers flowing away from the mountain peak. It's a mind-bending idea, and while it's not mainstream science, it's a compelling potential solution to one of cosmology's deepest puzzles. So, let's circle back to where we started. That feeling of your life moving in one direction. The shattered egg that never reassembles. We called the reason for this the universe's greatest mistake. But what we've found is something much deeper. That pristine, low-entropy state of the Big Bang wasn't a blunder. It was an inevitable consequence of gravity. It was the necessary blank canvas for the cosmos to create anything at all. The arrow of time that you feel so personally is the direct echo of that initial state. It's the sound of the universe on its relentless, gravitationally driven journey from perfect simplicity to the magnificent complexity of galaxies, stars, planets, and us. Your future isn't a mistake. It's the unfolding of a cosmic story that was written into the laws of physics from the very first moment. If you enjoy pondering the big questions of the cosmos, make sure to subscribe and ring that bell, because there are plenty more secrets of space and time to explore together. Physics says time can go backwards, so why can't we? Watch a glass fall. There's a quiet moment in the air, then the sound of it shattering on the floor. Now, imagine that moment in reverse. Shards of glass seem to remember their place, lifting from the ground to knit themselves back into a perfect whole. The wine, a dark stain on the rug, gathers itself and leaps upward, filling the reformed vessel as it settles silently back on the table. It feels wrong. It feels like something from a dream, an impossible magic. And yet, the most fundamental laws of our universe, the quiet rules that govern every particle and every force, work just as well forward as they do backward. The laws of physics say that a reversed film of a shattering glass is, in a way, just as valid as the forward one. So why are we all part of a quiet, one-way journey into the future? Why can't we unbreak an egg, or remember what will happen tomorrow? If the deep machinery of reality has no preference for past or future, why is our entire existence defined by a gentle, irreversible forward march? This is not a small question. It sits at the heart of science, a silent tension between the pristine mathematics of our theories and the most basic fact of our lives. That yesterday is gone, and tomorrow is not yet here. The answer, it turns out, is not hidden in some undiscovered rule that forbids time from moving backward. It is quieter, grander, and more elegant than that. The answer isn't in the laws themselves, but in how the universe began. To understand this, we have to look closely at the world around us. First, at the laws of physics that are mysteriously silent on the direction of time. Then, we must get to know a concept you have likely heard of, but may not truly understand: entropy. And finally, we must trace it all back to a single, extraordinary clue left over from the Big Bang itself, 13.8 billion years ago. A law for two directions. To truly appreciate the depth of this puzzle, we first need to see just how time-blind the fundamental laws of physics are. This isn't a fringe idea, it's a core feature of our most trusted theories. We call it time reversal symmetry. It means that if you take the equations describing how something works and you swap time, t, with negative t, the equations still hold true. The physics works just as well. Our journey begins with Isaac Newton. His laws of motion describe a clockwork universe. Imagine the solar system, a majestic, silent dance of planets orbiting the sun. We can use these laws to trace their paths perfectly. Now, if we reverse the calculation, the planets don't fly off into chaos. They perfectly retrace their orbits, moving backward along the exact same ellipses. Newton's laws are perfectly content with this reversed reality. Think of something simpler: two billiard balls colliding on a frictionless table. They approach, they touch, they bounce off in new directions. If you were to watch a film of that collision, could you say for certain if it was playing forwards or backwards? You couldn't. The reversed collision is just as physically plausible as the forward one. At this fundamental, mechanical level, there is no arrow of time. Let's move forward to the work of James Clerk Maxwell, who unified electricity and magnetism into a single theory of electromagnetism. His equations describe how light works, how radio waves travel, how charges interact. And just like Newton's laws, Maxwell's equations are time-symmetric. They describe light waves expanding outward from a source, like ripples from a stone dropped in a pond. This is what we always see. A light bulb radiates light outwards, filling a room. But the equations have another, equally valid solution. One where waves travel inward, converging from all directions onto a single point. We don't see this happen, not because the math forbids it, but simply because the universe doesn't seem to work that way. We never see scattered light from a room suddenly gather itself and pour back into the filament of a light bulb. But the laws themselves would allow it. The rulebook is neutral. Now for the 20th century, and the twin pillars of modern physics: Einstein's relativity and quantum mechanics. Einstein's theories paint a picture of spacetime as a unified fabric. Your life is a path, a world line, traced through this fabric. According to relativity, the laws governing this fabric are time-symmetric. Traveling forward or backward along your world line are equally valid from the perspective of the equations. For a particle of light, traveling at the ultimate speed limit, time doesn't really pass at all. From its point of view, the beginning and end of its journey are instantaneous. Then we dive into the subatomic world. The master equation here is the Schrödinger equation, which governs how a quantum system evolves over time. And, as you might guess, it is also fundamentally time-symmetric. The evolution of quantum possibilities is reversible. The laws that govern atoms, electrons, and quarks have no built-in preference for past or future. This is the heart of the mystery. From the classical mechanics of planets, to the electromagnetism of light, to the spacetime of relativity, and the quantum probabilities of the smallest particles, our most fundamental theories of reality are written in a language that doesn't distinguish between forward and backward. And yet, everything we experience suggests there is a profound difference. We age, we remember, we break things. It's as if the laws of a country permit driving on either side of the road, but every single car, on every highway, without a single exception, drives on the right. This isn't a coincidence. There is a quiet current directing the flow of traffic. And that current is our next subject of study: the slow unwinding. If the fundamental laws of physics are an impartial rulebook, then the arrow of time must come from somewhere else. Our story now turns to a concept so central to this mystery that it has been called the arrow of time itself. This is the second law of thermodynamics, and its core idea is entropy. You have likely heard the word entropy before, often described as disorder or randomness. That's a good starting point, but to truly understand its role, we need to go a little deeper. The second law of thermodynamics states that in any isolated system, the total entropy will never decrease over time. It can stay the same, but it is far more likely that it will increase. This is why heat flows from a hot object to a cold one, and never the other way around. It's why your coffee cools down, but never spontaneously separates into a hot layer and a cold one. It is the universe's quiet, one-way street. To understand why, we need to think about it in terms of simple probability. Imagine a bedroom that is perfectly clean. Every book is on its shelf, alphabetically. Every piece of clothing is folded. This is a highly specific, ordered arrangement. We can call this a low entropy state. Now, what does a messy room look like? The books could be on the floor. The clothes could be on the chair. There are thousands, millions of possible arrangements that would all qualify as messy. This is a high entropy state. If you simply live in your room for a week, what is more likely to happen? Will the room, by chance, remain in that one single, perfectly ordered state? Or will it drift into one of the millions of possible messy states? The room gets messy not because of a force of messiness, but because there are vastly more ways for it to be messy than for it to be clean. It's just statistics. Let's make this more precise with a deck of cards. A new deck is in a perfect, specific order. This is one single arrangement, a state of minimum entropy. Now, shuffle the deck. The number of possible arrangements for 52 cards is an 8 followed by 67 zeros, a number larger than the number of atoms in our galaxy. When you shuffle, you are just randomly rearranging the cards. But because there are trillions upon trillions of disordered arrangements and only one perfect one, you are statistically guaranteed to land in a disordered, high-entropy state. It's not that the laws of physics forbid the cards from shuffling back into perfect order. It's just so mind-bogglingly improbable that you could shuffle for the entire age of the universe and never see it happen. This is the secret of the second law. The universe doesn't have a preference for disorder. It's just that there are unimaginably more ways for things to be disordered than for them to be ordered. So as particles jiggle and jostle, following those time-symmetric laws, they are overwhelmingly more likely to stumble into a high-entropy configuration. Let's return to our first examples. An intact egg is a small miracle of low-entropy order. Its molecules are arranged in a very specific structure. When it hits the floor, that structure is destroyed. There is only one way for those molecules to be an egg, but there are countless trillions of ways for them to be a puddle on the floor. For the egg to unscramble, every single molecule would have to, by pure chance, move in a perfectly coordinated reverse path. It's not forbidden, it's just statistically impossible. This same principle explains memory. Why do we remember the past, but not the future? Creating a memory is a physical process that increases the total entropy of the universe. A memory is a record of a lower entropy state, the event, created as part of an entropy increasing process. We have records of the past because the past, by definition, was a time of lower entropy. We can't remember the future because the future is the direction of increasing entropy. You can't have a record of a state that is more disordered than your own. So, it seems we have found the source of time's arrow. It is the second law of thermodynamics, the inexorable march of the universe from order to disorder. But this understanding, as complete as it seems, leads to a much quieter and much deeper question. The second law explains why entropy increases, assuming it started low. But it doesn't explain why it was low to begin with. A state of high entropy is, by definition, the most probable state. If you were to look at the universe at a random point in its history, you would expect to find it in a state of maximum entropy, a dull, uniform soup. But that's not what we see. Our universe is like walking into a room and finding that a deck of cards, once shuffled, has arranged itself in perfect, new deck order. The law of shuffling explains why it will become disordered again, but it doesn't explain the breathtakingly improbable initial setup. Why was the universe's deck so perfectly stacked at the beginning? To answer that, we must go back to the origin of time itself. An echo from the beginning. We've established that the arrow of time emerges from the statistical tendency of things to move from order to disorder. But this led us to a deeper question. Why was our universe so incredibly ordered in the first place? The fact that the universe began in an extraordinarily low entropy state is the single most important part of this story. This idea is known as the past hypothesis. To understand it, we have to journey back 13.8 billion years to the Big Bang. We often picture the Big Bang as an explosion, a chaotic event. But from a thermodynamic perspective, the very early universe was a state of supreme, almost perfect order. It was a hot, dense, and, most importantly, incredibly smooth soup of particles and energy. This might seem counterintuitive. Isn't a smooth gas more disordered than a collection of complex galaxies? Not when you consider gravity. For a system governed by gravity, a smooth, uniform state is actually a very low entropy configuration. It's highly specific and therefore highly improbable. Gravity likes to clump things together. A smooth distribution of matter is like balancing a billion pencils perfectly on their tips. It's an ordered state, primed to collapse into a more disordered one. And that is what happened. In the moments after the Big Bang, gravity began to act on tiny fluctuations in that primordial soup. Regions that were infinitesimally denser began to pull in more matter. Over millions and billions of years, this gravitational clumping formed a vast cosmic web. Along these filaments, matter condensed to form the first galaxies, and within them, the first stars. This process, the universe going from a smooth, uniform state to a clumpy, structured state, is a process of increasing entropy. A star itself is an engine of entropy production. It takes low-entropy fuel, like hydrogen, and converts it into higher entropy products, heavier elements and a flood of heat and light that radiates out into cold, empty space. Every process we see, from the burning of stars to the emergence of life on Earth, is powered by this cosmic unwinding. Life itself maintains a local pocket of low entropy, our ordered bodies, by consuming low entropy energy, from the sun or food, and releasing high entropy waste, heat, increasing the total entropy of the universe. This is where the pieces of the story come together. The arrow of time we experience is an emergent, cosmological phenomenon. It exists for one reason. Our universe began in a highly specific, highly ordered, low-entropy state. Ever since that moment, the universe has been doing what is statistically most probable, moving toward states of higher and higher entropy. We are living in the unfolding consequences of that one primordial fact. The reason you can break an egg but not unscramble it, the reason you remember the past but not the future, can be traced back to the specific, smooth conditions of the Big Bang. We are all carried along on a great, cosmic current of increasing entropy that started 13.8 billion years ago. Of course, this raises the ultimate question. Why was the beginning so ordered? This is one of the deepest questions on the frontiers of modern cosmology. We don't have a definitive answer. Some physicists believe it might just be a fact of our universe we have to accept. Others turn to more speculative ideas like the multiverse. In this picture, our universe is one of countless bubble universes. The vast majority might start in a high-entropy state, existing as timeless, chaotic seas. But by pure chance, a tiny fraction might start in a low-entropy state like ours did. And since observers like us can only exist in a universe with an arrow of time, it's no surprise we find ourselves in one of these rare, ordered universes. Yet other theories, like cosmic inflation, suggest that the process that created our universe naturally produces a low-entropy starting point. The mystery, as always, continues, waiting patiently for our understanding to catch up. The current of probability. And so, we can bring our quiet investigation to a close. The mystery of why time only moves forward is not found in a secret direction written into the fundamental laws. Those laws remain beautifully, stubbornly symmetric. The answer is that the arrow of time is a statistical phenomenon, a consequence of the universe's journey from a single, improbable moment of extreme order 13.8 billion years ago. We can't go back in time for the same reason that a shattered glass doesn't reassemble itself. It is not because the individual movements of the particles are forbidden. It is because the coordinated, collective action required to reverse the process is so statistically astronomical as to be effectively impossible. To unscramble an egg, trillions of molecules would need to, by pure chance, reverse their chaotic dance and return to the single, specific state they once occupied. We are simply swept along by the current of probability. But is it possible that the fundamental laws aren't perfectly time-symmetric after all? Physicists have found very small exceptions. In the realm of subatomic particles, through the weak nuclear force, we have observed processes that do show a very slight preference for a direction in time. This is known as T-symmetry violation. However, and this is the crucial point, this effect is minuscule. It's a fascinating and important clue about the deepest workings of physics, but it is millions of times too weak to explain the overwhelming, everyday arrow of time we experience. The reason your coffee gets cold has nothing to do with the decay of subatomic particles. It has everything to do with the statistics of entropy. Finally, what does this relentless increase in entropy mean for the ultimate fate of the universe? If the arrow of time is defined by the universe moving from order to disorder, what happens when it runs out of order? The second law points toward a possible end state known as the heat death of the universe. This is a future, trillions of years from now, where entropy has reached its maximum. All the stars will have burned out. All black holes will have evaporated. All matter will have decayed into a thin, uniform soup, all at the same temperature. There would be no differences left to drive any processes. Nothing would happen. In a universe at maximum entropy, the arrow of time would cease to have any meaning. The past and future would be indistinguishable, a state of perfect, timeless equilibrium. We began with a simple observation. A broken glass doesn't put itself back together. This led us on a journey from our kitchen table to the very beginning of the universe. We found that the laws governing the smallest pieces of reality don't seem to care about the direction of time, but that our universe as a whole is governed by an overwhelming statistical trend toward greater entropy. We are on a one-way trip to the future, not because of a deterministic law, but because we are riding the unfolding wave of probability that began 13.8 billion years ago. Our perception of time's flow, our ability to remember the past, our sense of cause and effect, all of these are consequences of our cosmic inheritance. We are children of an extraordinarily low entropy past, living through its inevitable and glorious unwinding. The story of time is the story of the universe. It's a story that starts with an inexplicable state of perfect order and unfolds, through simple and impartial laws, into the rich, complex, and beautiful world we see around us. We are not just in the universe, we are a product of its history, and a part of its ongoing journey into the future. If this quiet exploration of time was something you enjoyed, consider liking the video and subscribing to the channel. And I'm curious to know, if you could revisit one moment in your past, not to change it, but just to observe it again, what would it be? Feel free to share in the comments below. Why your brain lies to you about time. Our experience of the world is governed by certain constants. The force of gravity, the speed of light, and the forward march of time. A second is a second. An hour is an hour. Yet, our perception of that passage can be inconsistent. An afternoon spent with friends can feel like a brief moment, while a 30-minute meeting seems to stretch into hours. It is a common experience, but not a mystery. It is a function of the brain. Our minds actively construct our experience of time, compressing it and expanding it. This is not a flaw in our biology, but a complex neurological process. By understanding the principles that govern our perception of time, we can gain insight into how we build the narrative of our own lives. The clock on the wall measures duration. The brain, however, tells a story. The grand illusion, debunking the internal clock. There is a common assumption that deep within the brain, there exists a single, centralized timekeeper, a biological metronome ticking away the seconds with precision. This idea is intuitive. Physical time is constant, and so our brains, it would seem, must have a mechanism for measuring it directly. This assumption, however, is incorrect. Neuroscience has found no single timekeeping center in the brain. What exists is a more complex and distributed system. Our internal sense of time is not a rigid stopwatch but an elastic measure, one that stretches and shrinks based on activity, emotion, and even physiology. This brings us to a fundamental distinction: the difference between physical time and psychological time. Physical time is the domain of physics. It is a rigid and measurable dimension of the universe, governed by principles like the Second Law of Thermodynamics. This is the arrow of time, where entropy or disorder moves in one direction. A broken egg does not reassemble itself. This creates a constant sequence of cause and effect, an objective reality measured by clocks. Psychological time is the time we inhabit. It is the brain's subjective experience of duration. This is the time that bends. 10 minutes waiting for an appointment can feel substantially longer than 2 hours spent absorbed in a film. The physical duration is different, but the perceived experience is inverted. Modern neuroscience suggests the brain does not perceive duration itself. It has no direct sensor for time. Instead, the brain perceives events in sequence. It registers change, and from that stream of information, it constructs a narrative. Recent research indicates our brains track time based on the accumulation of experiences, not by consulting a steady internal clock. We do not passively experience time flowing over us. We actively build the river, moment by moment, from the material of our experiences. The tools the brain uses for this construction, attention, emotion, and memory, are not precision instruments. They are biased toward narrative, and this is where the distortions begin. The attention factor, the distracted timekeeper. The most common distortion of time relates to one of the brain's most limited resources, attention. When the brain is deeply engaged in an activity, it can enter a state psychologists refer to as flow. This can occur during complex work, creative pursuits, or deep conversation. In these moments, the brain allocates nearly all of its available cognitive resources to the task. The regions of the brain responsible for self-monitoring and temporal awareness, such as parts of the prefrontal cortex, show reduced activity. The brain's executive functions are occupied. It is not that time itself accelerates. It is that the brain ceases to dedicate resources to tracking its passage. When we emerge from a state of flow and check the clock, the discrepancy between physical time and our psychological experience can be significant. For a period of hours, the brain was not creating a detailed temporal record. It was occupied with the experience itself. The opposite occurs during periods of boredom. Consider waiting in a quiet room with minimal stimuli. The brain, an organ evolved to scan and process information, is understimulated. In this state, it turns its attention inward. It begins to monitor itself and the passage of time with heightened awareness. Each second is registered. We become aware of the sound of ventilation, the movement of a clock's hands. Here, the elastic measure of psychological time is stretched. Because attention has no other significant object, it dedicates its resources to tracking duration. Every moment is catalogued and felt. This is why a short wait can feel exceptionally long, while an afternoon of engagement can seem to vanish. The determining factor is not the duration, but the allocation of attention. When playing a fast-paced sport, the mind processes a constant stream of variables: the position of the ball, the movement of other players. There is little capacity for temporal awareness. When holding a plank during a workout, however, the mind has few inputs beyond the physical strain and the desire for the exercise to end. In one scenario, attention is cast wide. In the other, it is focused on a single, sustained point. The resulting experience of time is fundamentally different. The emotional engine, how feelings bend reality. If attention is one great modifier of time, emotion is another, and its effects can be more powerful. Our emotional state changes the temporal physics of the mind. Fear, novelty, and awe all adjust the gears of our internal temporal sense. A clear example is fear. An individual in a car accident often reports that the event unfolded in slow motion. Time did not slow down. This is an illusion created by the interplay between the amygdala and the brain's memory systems. The amygdala is the brain's threat detection center. When it identifies a danger, it initiates a fight or flight response. It also signals other brain regions, particularly the hippocampus, to record as much detail as possible. In this state of high arousal, the brain gathers sensory data at an increased rate. It is like a camera switching from a standard frame rate to a high-speed one. The event itself does not last longer, but the memory formed of it is unusually dense. When the mind later plays back this memory, the high density of information gives it the quality of a slow-motion video. Because there are more frames of information packed into that short event, the brain concludes that the event must have taken a longer period to occur. The slow-motion effect is a retrospective illusion. The memory of the moment expanded, the moment itself did not. Pleasure and novelty have a different effect. These are associated with the neurotransmitter dopamine, which is linked to reward and motivation. The brain releases dopamine when we experience something new and enjoyable. A leading theory, the dopamine clock hypothesis, suggests that increases in dopamine effectively speed up our internal clock. Script Section 3. As the brain becomes engrossed in a rewarding, dopamine-fueled experience, it loses track of external time, similar to the state of flow. Awe can also alter time perception. When we observe something vast, a natural vista, a field of stars, our perception of the present moment can expand. Studies have shown that the experience of awe tends to make people feel as though they have more time. The profundity of the experience seems to slow down the brain's processing, creating a feeling of a fuller, longer present moment. Even body temperature may play a role. Some research suggests that a higher body temperature, as with a fever, can cause a perception of time moving faster, while a lower temperature can make it feel slower. This may be related to metabolic rates, as the chemical reactions that govern neural firing speed up with heat. Our experience of duration is not an objective measurement. It is a composite of inputs, influenced by fear, joy, awe, and even the temperature of our own blood. The memory paradox: short days, long years. The most consequential of the brain's temporal distortions is the memory paradox. This phenomenon explains why a vacation week can feel short while happening but long in retrospect, and why life seems to accelerate as we age. The key to this is the relationship between novelty and memory. Think of memory as a form of neurological archive. During a routine week, where one day is much like the next, the brain operates efficiently. It does not need to create a new, detailed file for each similar day. It can group them together, another workday. The number of new entries in the archive is small. Now consider a day spent traveling in a new country. Nearly every experience is novel: the food, the streets, the language. By the end of this single day, the brain has created hundreds of new records for its archive. Every new experience is deemed worthy of a detailed entry. This is the foundation of what is known as the holiday paradox. It has two parts. 1. During the experience, perspective view, asterisk. Constant engagement with new and exciting stimuli leads to a state of flow, where the internal sense of time runs fast. The days feel short. 2. After the experience, retrospective view, asterisk. When looking back, the brain accesses an archive for that period which is densely packed with unique memories. Because the amount of new data stored is so vast, the brain infers that the period must have been long. The week that felt short in the moment now seems like a rich, expansive chapter. The opposite is true for a month of routine. The days may have felt long due to boredom, but in retrospect, the entire period seems to contract. The brain has compressed dozens of similar days into a single, small file. With few unique data points to review, the month feels as if it disappeared. The days were long, but the month was short. This paradox is a primary driver of the feeling that time speeds up as we get older. The cause is not age itself, but the declining rate of novelty that often accompanies it. A year in the life of a child is filled with firsts. Their brain is in a constant state of recording. The density of new memories is enormous, and so the year feels vast. For an adult with an established routine, a year may contain far fewer firsts. Experiences are repetitive, so the brain compresses them. When looking back, there is less data to review, and the year feels as if it passed quickly. There is also a proportional aspect. For a 10-year-old, 1 year is 10% of their life. For a 50-year-old, it is only 2%. But the primary mechanism behind this acceleration is memory compression, fueled by a lack of novelty. The solution: hacking your perception of time. Our brains, then, are unreliable narrators of time. They construct our experience based on attention, emotion, and memory. Understanding this process, however, allows us to use these mechanisms to shape our own temporal reality. The objective is not to make every pleasant moment feel slow. The transience of joy is part of its nature. The goal is to build a life that, in retrospect, feels long and full. The goal is to arrive at the end of a year or a decade and find that it was a substantial period, not a blur that vanished. The method for achieving this is to cultivate novelty. If routine is the engine of temporal compression, novelty is the force of expansion. To slow down the retrospective perception of time, one must consciously and deliberately break routine. We must provide the brain with new experiences to create new memories. Each new memory is another anchor in time, another record in the archive of a life. This does not require dramatic upheaval. Novelty can be found in small, consistent acts. Take a different route to work, forcing the brain to navigate and observe. Prepare a new recipe, creating distinct sensory memories. Explore a new genre of music, visit a local museum, or learn the basics of a new skill. Each of these acts interrupts the brain's autopilot mode and engages its systems for learning and recording. It makes one day different from the last. In retrospect, these are the days that will stand out and give a life texture. A second, complementary tool is the practice of mindfulness. This is the deliberate act of paying close attention to the present moment. While novelty makes life feel longer in retrospect, mindfulness can make the present moment feel richer as it happens. When drinking coffee, focus on its warmth and aroma. When speaking with someone, put away distractions and listen. By directing full attention to the sensory details of the present, we signal to the brain that the moment is important. This deep engagement can make positive experiences feel more expansive and vivid. This leads to a different way of thinking about time. Physical time is an external measurement. Psychological time is the substance of our experience. The question becomes not, how much time do I have? But, how will I fill my time to make the record of it rich and dense? To bring it all together, the brain has no single clock. It constructs our experience of time using a distributed system. This system is influenced by attention, which makes time fly during flow states and drag during boredom. It is shaped by emotion, where fear can create an illusion of slow motion and dopamine can make time speed up. Script Section 3. Most critically for our long-term sense of a life, it is governed by memory. The brain creates a detailed record of novel experiences, making life feel long in retrospect, while it compresses routine, making years feel short. Time, then, is not something that simply happens to us. It is something our brain actively creates. This makes us the architects of our own temporal experience. The cosmic mistake that invented the future. The experience of time is a fundamental aspect of reality. We perceive it as a constant, directional flow, carrying events from an open future into a fixed past. This asymmetry, however, presents a profound scientific puzzle. The equations that describe most fundamental physical processes, from the orbit of a planet to the interaction of particles, exhibit a remarkable symmetry with respect to time. They function identically whether time moves forward or backward. While a subtle violation of this symmetry is known to exist within the weak nuclear force, this minor effect is insufficient to explain the powerful, unidirectional flow of time we observe. The origin of this arrow of time appears to lie not in the laws themselves, but in the state of the universe at its most distant beginning. The answer is found by examining three distinct, yet deeply interwoven, phenomena: the nature of memory, the behavior of physical systems, and the history of the cosmos itself. Together, they suggest the arrow of time as a relic of the universe's initial conditions. Our investigation begins with the evidence contained within human cognition. We experience a distinct asymmetry in our awareness of time, a phenomenon sometimes termed the psychological arrow of time. The past exists as a collection of recorded information, memories. The future, in contrast, is a realm of possibility, not yet recorded and therefore unknown. One can recall the details of a past event, but one cannot recall a future event with the same certainty. This subjective experience is grounded in a physical process. The formation of a memory involves a series of electrochemical signals that strengthen connections between neurons, creating a physical trace known as an engram. This act of creating an ordered neural structure requires energy and, in doing so, participates in a much larger universal process. The creation of local order within the brain is part of a system that, as a whole, contributes to an increase in the total disorder of the universe. Our internal sense of time's passage is not an illusion, but a reflection of a more fundamental, physical principle. This principle is our second area of study, the thermodynamic arrow of time. It is observable in countless systems, from steam dissipating into the air to the shattering of a glass. It is described by the Second Law of Thermodynamics, which states that in an isolated system, a quantity known as entropy will tend to increase over time. Entropy can be understood as a measure of disorder, or more precisely, a measure of statistical probability. It quantifies the number of ways the microscopic components of a system can be arranged without altering its overall macroscopic appearance. A highly ordered state, such as a room with every object in a specific place, corresponds to a very small number of possible microscopic arrangements. It has low entropy. A disordered state, such as a messy room, can be achieved through a near infinite number of different arrangements of its contents. Because there are vastly more ways for a system to be disordered than to be ordered, it is overwhelmingly more probable that it will evolve toward a state of higher disorder. This is not a force compelling systems toward chaos, but rather a statistical inevitability. The universe evolves from order to disorder because it moves from improbable states to more probable ones. This one-way journey is the thermodynamic arrow of time. Every physical process with a clear direction, including the biological processes of life and memory formation, is an expression of this law. Life creates temporary pockets of order, but it does so by consuming energy and increasing the total entropy of its environment. This observation leads to a necessary and profound inference about the universe's past. If entropy is always increasing, it implies that the universe in its past must have been in a state of even lower entropy, a state of greater order. Rewinding the history of the cosmos leads to a point of minimum entropy at its very beginning. To understand why, we must turn to our third and final phenomenon, written in the fabric of the cosmos. In the 1920s, observations by Edwin Hubble revealed that light from distant galaxies was consistently shifted toward the red end of the spectrum. This redshift indicated that these galaxies are moving away from us. Furthermore, the farther a galaxy is, the faster it recedes. The conclusion was that the fabric of spacetime itself is expanding. This provides the cosmological arrow of time, the direction of cosmic expansion, from a smaller past to a larger future. We can now identify three distinct directional processes: the psychological arrow of memory, the thermodynamic arrow of increasing entropy, and the cosmological arrow of an expanding universe. The central question for modern physics is whether the alignment of these three arrows is coincidental or indicative of a shared origin. The evidence strongly supports a shared origin, the Big Bang. The expansion of the universe implies that if its history is reversed, all matter and energy were once concentrated into an unimaginably hot and dense state. The thermodynamic arrow implies this initial state must have been one of incredibly low entropy, of improbable order. The entire history of the cosmos since has been the story of its journey from that ordered beginning toward a more probable, disordered future, unfolding within an expanding spacetime. This is often referred to as the past hypothesis. A fraction of a second after the Big Bang, the universe was a searingly hot plasma. Importantly, it was also almost perfectly uniform. From a gravitational standpoint, this smooth state represents a condition of very low entropy. In contrast, the universe today is highly structured, or lumpy. Matter has coalesced under gravity to form galaxies, stars, and planets, separated by vast voids. This structured state, perhaps counterintuitively, has a much higher gravitational entropy. The initial, low-entropy configuration of the universe was a wild statistical improbability. This single fact is the engine for the arrow of time. Because the universe began in such a highly ordered state, it possessed the potential for change. The second law of thermodynamics dictates that entropy must increase, and the Big Bang provided the low-entropy starting point that enabled this process to drive the universe forward. Cosmic expansion is integral to this process. As space expands, it creates more possible configurations for matter and energy, constantly increasing the maximum possible entropy the universe can hold. This ensures the universe has a vast potential for continued evolution toward disorder. When gravity pulls matter into a star, it creates local order. However, for a star to shine, it must radiate enormous amounts of energy into the cold, expanding void of space, an act which vastly increases the universe's total entropy. The expansion and the increase of entropy are interconnected processes, both initiated by the unique conditions at the universe's birth. It becomes clear that these phenomena are not independent. The unidirectional nature of time as we experience it is a direct consequence of the universe originating in a state of profound and statistically improbable order. A broken object does not reassemble because that would represent a decrease in entropy, a reversal of the overarching thermodynamic gradient established 13.8 billion years ago. Our brains form memories of the past, not the future, because the physical act of memory formation is itself an entropy-increasing process, carried along by this same cosmic current. The future exists as a realm of possibility only because the past was so exceptionally ordered. The improbable initial state of the universe provided the gradient down which time could flow. Without this condition, there would be no potential for change, no structure, no life, and no consciousness to contemplate the nature of time. The question of why the universe began in this special state remains a subject of intense scientific inquiry. Theories such as cosmic inflation propose mechanisms that could have produced these initial conditions. Other, more speculative ideas consider our Big Bang as one event in a larger multiverse. What is known is that the fundamental experience of past and future is an inheritance, a physical consequence of the unique state in which our universe began. The law that forbids time from reversing. You have never seen this happen. Not once. A shattered glass on the floor will not gather its 1,000 pieces, flying back into your hand to become whole again. Smoke will not retreat from the air, funneling back into the tip of a match that is no longer burned. An egg, scrambled in a pan, will not uncook, separating back into its yolk and white, nestled inside a shell that has miraculously reformed. There is a sense that these things are not just unlikely, they are impossible. They seem to violate a quiet, deep understanding of how the world works. For us, Time moves in one direction, like a river flowing from the past, through the present, and into the future. But here we find a profound paradox, one that sits at the very heart of physics. For the fundamental laws that govern every particle in that glass, every molecule of smoke, every atom in that egg, running the story backward is just as valid as running it forward. The laws of gravity, of electromagnetism, the strange rules of the quantum world. They do not have a preference for the future over the past. To them, the directions are interchangeable. So, what is it that stops time from reversing? What is the rule, the law, that prevents the tide from turning back? It is not a suggestion or a guideline. It is a single, fundamental law of the universe that acts as a gatekeeper, locking reality on its forward path. This is a journey to understand that law, and to see how a simple broken glass is connected to the very beginning of time itself. The one-way river. Let's stay in our familiar world for a moment, because the mystery begins right here. It's a quiet, constant feature of our reality, so familiar it often goes unnoticed. Time's unwavering direction. We remember the past, but we cannot remember the future. We can build a sandcastle, but we cannot unbuild it by simply waiting for the ocean to pull its waves back. We are born, we age, and we pass on. The sequence is never reversed. This shared, universal experience is what physicists call the arrow of time. It is the consistent direction we see in every unfolding event. It is the reason a cup of hot coffee will always cool, sharing its warmth with the room around it. But a lukewarm cup will never spontaneously draw heat from the air to become hot again, leaving a cold patch in its place. Every process we witness seems to have an indelible stamp of before and after. Cream can be stirred into coffee, its white clouds blooming and dissolving into a uniform light brown. But no amount of stirring in the opposite direction will ever coax those complex, wispy patterns to reappear. This might seem obvious. Of course, that is how it works. But inside that feeling of course, is where the true mystery is hiding. Our intuition tells us that these processes are irreversible. And yet, the bedrock of our physical world, the very equations that describe the dance of particles, tell a different, and quietly strange, story. A story that suggests the one-way river we all experience is something other than a fundamental rule of motion. A story that forces us to ask a difficult question. If the laws of physics don't forbid it, why do we never see time move backward? The physics paradox. To explore this mystery, we must look at the first clues, which are found not in the everyday, but in the silent, fundamental rules that govern existence. Imagine we are watching a simple physical event. A planet orbits a star, held in its path by gravity. If we run the film of this event backward, what we see is a planet orbiting a star. Nothing seems wrong. The reversed motion is perfectly in line with the law of gravity. Let's try another. A perfectly elastic ball bounces, with no air to slow it down. Forward, it bounces. Backward, it bounces. Again, nothing looks out of place. The laws of motion described by Isaac Newton are perfectly content with time flowing in either direction. This property is called time reversal invariance or T-symmetry. It is not just a feature of older physics. It remains true in Einstein's theory of relativity. It holds for the laws of electromagnetism that govern light and energy. And with a few very faint exceptions, it even holds true for the strange and wonderful world of quantum mechanics. At the most fundamental level we can perceive, the universe does not seem to have a built-in forward button. The equations that describe how particles interact are just as valid if the value for time is positive or negative. A film of two electrons repelling each other, when played in reverse, simply looks like two electrons approaching one another. No law is broken. And here is the central paradox. On one hand, we have the overwhelming evidence of the world we see and touch, the world of eggs and coffee, where time's arrow is absolute. On the other hand, we have the microscopic world of particles, where the fundamental laws are almost entirely time-symmetric. It is a profound mismatch between the rules and the reality we observe. It is like discovering a rule book for a game that says pieces can move forward or backward, but then watching millions of games where every player, without fail, only ever moves their pieces forward. You would begin to suspect there must be another rule you haven't found yet. A larger rule, one that governs the entire game, not just the individual pieces. So if the basic laws of motion don't dictate a direction, why does everything we see move as if they do? What is this hidden rule that corrals all of those time-symmetric interactions into a one-way flow? The answer is found not in gravity or motion, but in the science of heat, chaos, and probability. The answer is the second law of thermodynamics. The gatekeeper appears. Here we find the principle that dictates the forward arrow of time. The second law of thermodynamics. The name may sound complex, but the core idea is beautifully simple. It can be captured in a single word: entropy. In simple terms, entropy is a measure of disorder or randomness. A system with low entropy is ordered and structured. A system with high entropy is disordered and random. Think of a room. When it is clean and tidy, with every book on its shelf, it is in a state of low entropy. When it is messy, with things scattered about, it is in a state of high entropy. The second law of thermodynamics makes a simple, yet unbreakable statement. In an isolated system, one that isn't exchanging energy with anything else, the total entropy will always increase, or stay the same. It will never decrease on its own. This is the law that forbids time from reversing. A clean room, left to itself, will tend toward messiness. That is an increase in entropy. A messy room will never spontaneously clean itself. That would be a decrease in entropy, which the second law does not allow. Heat flows from a hot coffee to a cool room because the energy is more disordered when it is spread out. That is an increase in entropy. An ice cube melts because the organized, crystalline structure of the ice gives way to the chaotic, free-moving state of liquid water. An egg breaks, and its highly ordered internal structures become a simple, disordered puddle. In every case, entropy increases. The arrow of time, the one-way street we experience, is nothing more than the universe's quiet, relentless journey from order to disorder. Time flows in the direction of increasing entropy. The past is the past because it was a state of lower entropy. The future is the future because it will be a state of higher entropy. This law is different from the others. It is not about how a single particle behaves. It is a statistical law about the collective behavior of countless particles. And to understand why this statistical rule is so powerful, why it is the undisputed gatekeeper of time, we have to look at what disorder truly means. It isn't just about messiness. It's about probability, the unwinnable lottery of time. Why is the journey towards disorder so inevitable? The answer is found in simple statistics. The secret is that there are vastly, almost incomprehensibly, more ways for a system to be disordered than for it to be ordered. Imagine a box containing 100 molecules of gas. We can start them in a state of improbable order, for instance, all of them gathered in one small corner. This is a low entropy state. Now, we let them move. They will quickly spread out, filling the entire box, moving from that single, ordered state to a disordered, high entropy state where they are distributed more or less evenly. But why? It's not because a new force pushes them out of the corner. The laws of motion for any single molecule are time-symmetric. It could just as easily bounce back into the corner as out of it. They spread out for a purely statistical reason. Think about all the possible ways those molecules can be arranged. The arrangement where they are all in one corner. There is essentially only one way for that to happen. Now, think about the number of arrangements where they are spread throughout the box. The number of ways to achieve that disordered state is astronomical. The system doesn't want to be disordered. It simply moves into the state that is overwhelmingly more probable. Because there are trillions upon trillions more disordered arrangements than ordered ones, the system is almost certain to end up in one of them. For all 100 molecules to spontaneously move back into that corner at the same time, it is not, in the strictest sense, impossible. But the odds are so small that you would have to wait for lifetimes of the universe to pass to see it happen. It is statistically indistinguishable from impossible. Consider a new deck of 52 cards, sorted by suit and number. This is a perfect, low-entropy state. There is exactly one way for the cards to be in this order. Now, shuffle the deck. It is now in a more disordered, higher entropy state. The number of possible shuffled arrangements is 52 factorial. An 8 followed by 67 zeros, a number far larger than the number of atoms in our galaxy. Every time you shuffle, you are randomly picking one of those arrangements. The chance that you will magically return the deck to its original, perfect order is 1 in that staggering number. The system moves from order to disorder because disorder has an overwhelming statistical advantage. There are simply more ways to be messy. This is the engine behind the second law. A broken egg will not reassemble because the number of ways its molecules can be arranged as a messy puddle is astronomically greater than the number of ways they can be arranged in the complex structures of a whole egg. The arrow of time is carried forward on a vast, silent tide of probability. But this leads to an even deeper question. If the universe is always moving from order to disorder, it must mean something extraordinary about its beginning. If entropy is increasing today, it must have been lower yesterday. Tracing this logic all the way back, we arrive at an astonishing conclusion. The universe must have begun in a state of the most perfect order imaginable. The cosmic anchor. This journey, from a broken glass to the laws of probability, leads us to the very beginning of time. The second law of thermodynamics is not just a local rule, it applies to the entire universe. And if the universe's total entropy is always increasing, we are forced to ask, what did it look like when it was fully wound? The answer lies at the moment of the Big Bang. According to our best understanding, the universe began around 13.8 billion years ago in an incredibly hot and dense state. But crucially, it was also a state of extraordinarily low entropy. This may seem strange. How can a searing fireball be ordered? We often think of order as complex structure, like a snowflake. But in this context, order also means uniformity and smoothness. The early universe was astonishingly uniform. Its energy and matter were distributed almost perfectly evenly. This initial low-entropy state is the ultimate anchor for the arrow of time. This is sometimes called the past hypothesis. The reason time has a direction, the reason entropy increases today, is because the universe was born in this special, highly ordered condition. It was as if the universe began with its deck of cards in perfect, new deck order. For the last 13.8 billion years, the cosmic shuffle has been underway, and entropy has been increasing ever since. The expansion of the universe itself drives this process. As space expands, it creates more room, more ways for things to be arranged. Gravity pulls matter together to form stars and galaxies. This might look like an increase in local order, but the process releases enormous amounts of heat and radiation into the vast emptiness of space, dramatically increasing the total entropy of the universe. Life itself is part of this story. Living beings are islands of incredible, low-entropy complexity. But we maintain this order only by taking in low-entropy energy, like food and sunlight, and releasing high-entropy waste, like heat. We fight a local battle against entropy, but our very existence contributes to its overall increase in the cosmos. So, the arrow of time is a direct consequence of the initial condition of our universe. We remember the past and not the future because the ultimate past event, the Big Bang, was a moment of special, improbable order. And where is this all headed? If the trend continues, the universe moves toward a state of maximum entropy, sometimes called heat death. A future where all the stars have burned out and all that remains is a cold, uniform soup of particles. In this state, nothing would happen. The arrow of time would lose its meaning, because entropy could no longer increase. Quantum wrinkles and the impossibility checklist. Our story has led us to a powerful conclusion. The arrow of time emerges from the relentless increase of entropy, a process anchored by the ordered beginning of the universe. But there are a few final, strange clues to consider from the quantum realm. We said that the fundamental laws are almost entirely time-symmetric. At the subatomic level, the weak nuclear force, which is involved in some forms of radioactive decay, does in fact violate this time reversal symmetry, but only slightly. The effect is a faint whisper, far too small to explain the immense, universal arrow of time we observe. It is a fascinating clue that time may have a slight intrinsic direction, but it is not the main driver. Physicists also speak of a deeper, combined symmetry known as CPT symmetry, for charge, parity, and time. The idea is that if you take any physical process, swap the particles with their antimatter counterparts, charge, view it in a mirror, parity, and run it backward, time, the result should be indistinguishable from the original. This symmetry is believed to be exact, telling us that time is interwoven with the fabric of space and matter in ways we are still trying to understand. But it offers no simple way to reverse time's flow. So, what would it truly take to make time go backward in our reality? First, it would require reversing the initial conditions of the universe. We would need a universe that began not in a smooth, low-entropy state, but in a chaotic, high-entropy state, and then somehow evolved toward perfect order. This would mean reversing the very logic of probability that underpins our world. Second, it would require a fundamental violation of the second law of thermodynamics on a cosmic scale. A new law of nature would be needed, one that forces systems to move from states of high probability to states of astronomically low probability. Every random motion of every particle would have to conspire, against all odds, to create order from chaos. Finally, it would likely require a reversal of the universe's expansion. The expansion of space provides an ever-growing canvas for disorder to flourish. Our current observations suggest the opposite is happening. The expansion is accelerating, pushing the universe further toward maximum entropy. This shows us why time reversal remains in the realm of fiction. Reversing the arrow of time would demand a completely different universe, one with a different origin, different statistical laws, and a different cosmic destiny. We began with a simple observation: a broken glass that cannot reassemble itself. We end with the vast expanse of cosmic history. We have found that the one-way flow of time is not a rule written into the laws of motion for a single particle. It is an asterisk emergent property. It emerges from the statistical behavior of countless particles, all guided by the quiet, unwavering logic of probability. The laws of physics for a single atom may not have a past or a future. But a universe full of atoms does. The arrow of time is the arrow of increasing entropy. It is the story of the universe moving from its special, low entropy beginning toward the trillions upon trillions of disordered states that lie in its future. It is a story written not in stone, but in statistics. And on a cosmic scale, those statistics are destiny. So the next time you stir cream into your coffee, take a moment. You are not just witnessing an everyday event. You are watching a direct consequence of the Big Bang. You are seeing the unfolding of entropy, the very engine that powers the river of time. The reason you can remember putting the cream in, but cannot remember it unmixing, is because you live in the expanding, cooling, and ever more disordered aftermath of that one singular, extraordinary moment that set the clock of our universe in motion, on a forward-only path. If this journey into the nature of time sparked your own sense of wonder, consider subscribing. We explore profound questions and cosmic mysteries like this one, breaking down the biggest ideas in science. And let us know in the comments, What is another deep question about the universe you would like us to explore together? What if time suddenly stopped everywhere? We tend to perceive the flow of time as a given. It is a silent, invisible constant, carrying existence from one moment to the next. But what if that constant suddenly ceased? What if the progression of time stopped, not just for an individual, but for everything, everywhere? It is a concept often framed as the ultimate form of control over reality. The consequences, however, would be far from a fantasy. The moment time stopped, you would not become an observer in a silent, frozen world. You would not walk among static forms as if in a museum of the present moment. The reality is that you would be instantly without sight, without sound, and trapped within a universe that has, in any meaningful sense, ceased to exist. To understand why, we must first break down what it would mean to pause the universe. Let us begin with the most immediate effects. Imagine it happens now. One moment, you are processing this information, and the next, time has frozen. The first thing you would not experience is darkness. The ability to see depends on photons, particles of light, traveling from a source, reflecting off objects, and entering your eyes. This journey requires time. In a frozen universe, every photon is fixed in its position. The light that was en route to you is suspended, and the light that had yet to be emitted will never be. You would see nothing, not because light is absent, but because it can no longer move. The silence would be absolute. Sound is our perception of pressure waves moving through a medium. This propagation is a process that unfolds over time. When time stops, these waves are frozen. The air molecules that were about to vibrate are now static. The world would be without sound, a quiet so profound it is not merely the absence of noise, but the absence of the possibility of noise. Movement would be impossible. Even thought would cease. The human body is a system of constant change. Respiration occurs as the diaphragm contracts and expands. The heart beats through a sequence of electrical signals and muscle contractions. Thoughts themselves are the result of electrochemical signals passing between neurons. All of these processes, breathing, circulation, thinking, are defined by change over a period of time. If time stops, so do they. The air you were about to inhale would become an impenetrable wall of fixed molecules. The chemical reactions that power your muscles would halt. The electrical impulses in your brain would freeze in place. In that single, eternal instant, you would not be a conscious observer of a static world. You would be a part of it. Your final thought would be an unfinished signal in a brain that will never fire again. There is no observer without the flow of time. This state would extend to everything. A bird would be frozen mid-flap, its wings locked against an unmoving wall of air. An ocean wave would be a perfect, glassy sculpture. The Earth's own rotation and its orbit through space would instantly stop. The law of conservation of momentum would be broken. Even more fundamentally, the universe would reach absolute zero. Temperature is a measure of the motion of atoms. It is the vibration of the universe's constituent parts. If time stops, all motion stops. The atomic dance ceases, and with it, all thermal energy vanishes. It would be a universe of ultimate cold and stillness. The fantasy of stopping time is, in its purest form, a scenario of universal cessation. It is not a pause button, it is a stop button with no possibility of recovery. This scenario, however, breaks the known laws of physics. It presents a paradox. So, let us modify the rules. What if time stops for everything in the universe, except for you? You are now a conscious, moving entity in a world where everything else is frozen. This is the classic thought experiment. Physics, however, presents a series of intractable problems. Let's revisit sight. For you to see an object, photons that have bounced off it must travel to your eyes. But those photons are frozen in time. If you move your head into the path of a photon, what would you see? A photon's energy is tied to its frequency, its vibration over time. A frozen photon has no frequency. It carries no energy. It would be like trying to see with a particle that has no energetic properties. You would remain blind. Now consider movement. To walk, you must push air molecules out of the way. In a normal environment, air is a fluid. But in a frozen world, the molecules of nitrogen and oxygen are locked in a rigid lattice. The air would be as solid as a diamond. Trying to move through it would be impossible. You would be encased in a prison of stationary air. Let's add another modification. A small bubble around you where time flows normally, allowing you to breathe and move. Even then, stepping outside this bubble would mean colliding with that solid wall of frozen air. You could exist within your personal sphere of time, but you could never leave it. Interaction itself becomes a paradox. To touch a frozen object, the atoms in your fingers must interact with the atoms of the object through the exchange of forces. But force propagation, like gravity or electromagnetism, takes time. These forces travel at the speed of light. In a frozen world, they cannot propagate. You could not feel the object, just as you could not push it. You would exist in the same space, but in a separate reality. This leads to an even deeper problem: a breakdown in causality. Albert Einstein's theory of special relativity is built on the principle that the laws of physics and the speed of light in a vacuum are constant for all observers. Your exemption from frozen time violates this. From your perspective, you could traverse the universe in an instant, achieving a speed that is effectively infinite relative to the frozen world. The laws that govern reality are an interlocking system. Attempting to stop one component, time, causes the entire machine to fail. The fantasy of stopping time misunderstands what time is. We imagine it as something separate, a clock that can be paused. But time is woven into the fabric of space-time, inseparable from space and the laws of energy and matter. To understand why it cannot be stopped, we have to ask a deeper question. Why does it move forward at all? We experience time's flow as a one-way progression. The past is recorded, the future is unknown. Yet, one of the deepest mysteries in physics is that the fundamental laws governing gravity, electromagnetism, and the nuclear forces are time-symmetric. They work equally well forwards as they do backwards. A video of two billiard balls colliding is just as plausible in reverse. So if the underlying rules have no preferred direction, where does our one-way experience of time come from? The answer appears to lie in a concept known as entropy. Entropy is a measure of disorder or randomness. The second law of thermodynamics states that in an isolated system, total entropy can only increase or stay the same, it never decreases. There are far more ways for a system to be disordered than ordered. A deck of cards, when shuffled, will almost certainly move to a more random state. An egg can be scrambled, but a scrambled egg will not spontaneously reassemble itself. This constant, irreversible march toward disorder is what gives time its arrow. The thermodynamic arrow of time points in the direction of increasing entropy. The future is the direction of greater disorder. The past is the direction of greater order. We remember the past because it is the low entropy state that contains information, the cause, while the future is the high entropy state where that information has dispersed, the effect. This arrow is cosmological, tied to the beginning of our universe. The Big Bang theory posits that the universe began in an incredibly hot, dense, and crucially, low entropy state. This may seem counterintuitive. However, in a universe dominated by gravity, a smooth, uniform distribution of matter is actually a state of very low entropy. A high entropy state would be one where matter has clumped together into black holes. The universe began with its entropy dial turned down. For the past 13.8 billion years, it has been expanding, cooling, and becoming more disordered. This expansion, the cosmological arrow of time, drives the increase of entropy, and the increase of entropy defines the forward direction of time. The two arrows point in the same direction. Even the creation of ordered structures like stars and living beings does not violate this law. Life is a temporary pocket of order, created and sustained by consuming low entropy energy and radiating high entropy waste in the form of heat. The process of creating this local order increases the total disorder of the universe as a whole. Time flows forward because the universe is, in a sense, progressing towards a state of greater randomness. This leads to a profound conclusion. If the arrow of time is defined by increasing entropy, what happens when entropy can no longer increase? What happens at the end of time's river? The journey of our universe, dictated by the march of entropy, points toward a final state known as the heat death. This is a future so distant it challenges comprehension. We enter an era far beyond the life of our sun. In about 100 trillion years, the last stars will have exhausted their fuel. The universe will become a vast, dark expanse, populated by the remnants of stars, black holes, neutron stars, and cold black dwarfs. Over even greater timescales, galaxies will dissolve, their contents scattered or consumed by supermassive black holes. For a time, these black holes will be the last major structures. But they are not eternal. Stephen Hawking showed that black holes slowly leak Hawking radiation. Over unimaginable eons, a timescale on the order of 10 to the power of 100 years. So long that the current age of the universe is a rounding error by comparison. Even the most massive black holes will evaporate. With the end of the last black hole, the universe enters its final phase, the dark era. It has reached maximum entropy. It is a vast, cold, nearly uniform soup of stray particles. This is the state of heat death. The temperature is uniform, just above absolute zero. No energy gradients remain, so no work can be done. Nothing happens. In this final, desolate state, the arrow of time becomes meaningless. Since the universe is already at its maximum state of disorder, entropy can no longer increase. The law that defined the forward direction of time ceases to apply. Time does not freeze, it becomes directionless. The distinction between past and future dissolves. Without change, there is no way to differentiate one moment from the next. The passage of time ceases because the universe has become permanent. However, even at the edge of this absolute end, some speculative ideas in physics offer a different possibility. The first is a concept from quantum mechanics known as Poincare recurrence. This theorem suggests that in a closed system, given enough time, the system will eventually return to a state close to its initial one. In theory, after an almost infinite duration, random quantum fluctuations in the empty void could cause a spontaneous decrease in entropy, potentially triggering a new, low-entropy state, a new Big Bang. The arrow of time could restart. The estimated time for such an event is so vast, however, that it is practically indistinguishable from an eternity. There is another, more unusual idea, proposed by the physicist Julian Barbour, which he calls the Janus point. In this model, the Big Bang was not a beginning, but a central point of maximum order. Time does not flow from the Big Bang, but away from it in two opposite directions. From this single moment, two distinct universes expand outward, each with its own arrow of time pointing away from that shared, central past. This would imply the existence of a twin universe on the other side of our Big Bang, where time runs backwards relative to ours. This is a concept at the frontiers of theoretical physics and is far from proven. Our journey began with a simple question: what if time stopped? We found that it cannot. Time is not an external mechanism. It is an emergent property, a consequence of the universe's fundamental journey from order to disorder. The flow of time is powered by the universe's irreversible increase in entropy. The initial scenario of being trapped in a frozen world is impossible because time is too deeply woven into reality. You cannot pause light, sound, and motion without also pausing the consciousness that would perceive them. The true insight is not that we are prisoners of time's flow, but that we are its products. The increase in entropy is what allows stars to shine, what drives chemical reactions, and what makes the complex processes of life possible. The arrow of time is not a cage, it is the force that enables existence. Its forward motion gives us past, present, and future. We live in a fleeting moment of cosmic history, an era where there is still enough order for stars to form, for planets to gather, and for life to contemplate the nature of time itself. For now, the arrow points forward. And in that forward motion is the potential for everything we know.